Hey, good evening and welcome everybody. We're back. We're doing more chemistry reactions. I really was not planning on doing this week. I was kind of planning on being like, oh, have a nice little 2-stream week, to reintroduce myself back to things after the extended break I had and the whole convention attendance I went and did. And then all of a sudden, just two things that I commonly like to react to hit my sub box, and it's like, well, I really can't turn down an opportunity like that. So all of a sudden we're going to be talking about industrial safety and home chemistry in your Australian crack shed. So it's 2 different kinds of safety disasters, both related, but still all along the same vein. Alright, well, I feel like we should probably get started with the U.S. Chemical Safety Board video, because the U.S. Chemical Safety Board video is like 20 minutes long, whereas the Extractions&Ire video is like an hour and 5 minutes long. So I think there's a good chance we get through one a lot faster than the other, and I feel like doing that, less switching to do later on. So I guess that's enough waffling to let people maybe roll in for a little bit. So yeah, let's switch on over. My little handy dandy notepad on the side so we can draw some stuff, talk about chemistry. And let's see what we got. For anybody unfamiliar, I guess I should explain. For anybody who is new to the channel, unfamiliar with some of the things I react to, the U.S. Chemical Safety Board is an official independent agency of the U.S. government that is tasked with investigating industrial disasters. This sounds boring as hell, but their YouTube channel is actually gas. They have very high-quality animations for their work, and they often take on this true crime feel to them because of the fact that usually what's the cause of a big industrial disaster with somebody dying is management neglect, or nobody thought to check on, this piece of the piping that has been left alone for 27 years. And it's this fun kind of investigative thing with the crux is that there's some kind of mystery to what happened. It's great. I love watching these, even though how boring they might sound. And oh yeah, I am a chemist and a lab safety person. So this is up my alley in 2 ways.
December 8th, 2020. The Optima
nice
Bell
lighting.
Chemical Facility in Bell, West Virginia. 1 employee was killed and 2 others were evaluated for respiratory irritation when a pressure vessel exploded, causing a fire and toxic chemical release.
Sorry. 2 people died. 1 had maybe some respiratory irritation. That poor 1 person.
The report identifies several factors that led to this tragedy. In particular, we have found that gaps in existing regulations do not adequately protect against hazards presented by reactive chemicals. This long-standing safety gap must be addressed.
All right, so now they're going to explain. How did it all start? Where did we go so wrong?
Optima Bell is a toll manufacturer, or
Toll?
a company contracted to provide chemical processing services, typically using its own equipment.
Huh.
On the day of the
Okay.
incident,
All right.
Optima
So I guess okay. In my idea, that would be like somebody who you place a quote with to get chemical manufacturing done, or maybe somebody who you try purchasing through some vendor, and then they actually do the contracting to this place. All right. Well, maybe that sounds a little bit disconnected from the final product, but hey, this actually looks pretty good. You can even see there's detail on that guy's face in the background.
Bell was working on behalf of Clearon Corporation to conduct a batch tolling operation. The tolling operation involved Optima Bell dehydrating a chemical called CDB56.
CDB56. That's okay.
CDB56 is a white powder that is used as a source of chlorine for cleaning and sanitizing products.
Actually, let me draw that real second. Sorry to rewind, but I would like to have that for my own reference when we get into the actuality of the disaster, for what happened. I'd like to be able to maybe predict the future a little bit. NCl CON Cl again, and then there we go. Oh, and then sodium. Well, it's not really a bond. It's important, kids. Your ions don't actually form bonds. They're just electrostatically attached to each other, or drawn to each other. Okay, interesting. And they said it's a chlorine source. It looks very similar. It's actually very similar to a compound they talked about last time they did a chemical disasters video on TCCA, trichloroisocyanuric acid. It's a very close structure, so I could see why these NCl bonds are very weak, and so it's used for chlorine generation.
CDB56 is a white powder that is used as a source of chlorine for cleaning and sanitizing products. When CDB56 is exposed to high heat, it can decompose and release chlorine and other toxic substances.
Let me cook my CDB56 on the stovetop.
To dehydrate CDB56 to transform it into a different compound that Clearon calls CDB63.
Oh goodness.
CDB.
That's entirely different. Okay, so they wanted to
call CDB63.
Wait, what? Wait, how did the structure change there? So the bonds went that way. That's not a That's not a different structure. That's a different isomer. Or not a different isomer. That's a different what's it called when the electrons switch places again? It's a different resonance structure. I mean, I guess the sodium technically moves, but I would think that the O and the oxygen and the nitrogen be sharing that charge anyways. That's why that's confusing. Nothing really changed, and that's not a dehydration reaction.
Transform it into a different compound that Clearon calls CDB63. CDB63 is a white granular material that is used for water chlorination in swimming pools, as well as in detergents and bleaching agents.
Yes, generic laundry detergent,
like
my favorite.
CDB56, it can also decompose and release toxic chlorine when heated. For the batch dehydration process, Optima Bell planned to use a type of pressure vessel called a rotary double cone dryer. Clearon, however, had never before used this particular kind of dryer for dehydrating CDB56.
Well, that's not a good idea.
Therefore,
hey, Bingo
Optima
Bongo.
Bell developed a new procedure for the dehydration operation.
They're talking about, I don't know how much you've missed, but they're currently talking about dehydrating this molecule on screen, and they've never in fact used this This company has never, in fact, used this instrument before for doing this dehydration.
Their plan was to heat the compound by applying
And thanks for the welcome
steam
wishes.
to the
It's good to be
jacket
back.
of the rotary double cone dryer, while the dryer rotated to tumble the contents inside. And equipment would
Slower
be used
rotation,
to create
but
vacuum
kind of a
conditions
stir.
in the dryer
Ooh.
to help remove any gases produced, such as water vapor. Automobile,
I guess if it's
however,
slow
did
enough, you
not
could do that without
realize
sucking out
that
smoke.
Heating CDB56 inside the dryer could cause the compound to decompose.
Ah, they weren't
On
aware of the
December
chlorine
8th,
generation.
2020, Automobile employees started the first of 4 planned batch operations to dehydrate the CDB56. They applied heat to the dryer, and workers from both Automobile and Clearon monitored the progress. But by late afternoon, workers observed some operational problems. They stopped the dryer to troubleshoot.
This
About
part
an
is
hour
only in black
later,
and white.
they
I told that
restarted
thing
the
to print
dryer's
color.
rotation, and steam was reintroduced to the dryer's jacket. But problems persisted. A sample of material taken from the dryer around 7:30
It's like kitty litter.
p.m. showed that moisture levels of the compound were not decreasing as expected. And now
Yeah.
the white material contained dark specks. After Automobile texted Clearon about the issue,
Again, I feel like there's something wrong with what they're talking about or the reaction they're trying to accomplish here too, because it's definitely not a dehydration reaction. You can't dehydrate this compound. Well, okay, no, actually, I think I see what they were. Okay, so I neglected to. That's right. Okay, so they drew 2 extra H2O molecules, like with this way back at. Okay, where am I? 355. Yeah, back here originally. But I didn't take that seriously because I don't tend to consider a hydrate a different substance, more or less. But I guess in this very specific instance, if you actually heat and get rid of those separate waters, that would cause that isomerization and would actually cause the sodium to move down here. And the charge to also move with it. Huh. Interesting. I guess. Huh. Yeah, no, okay. You know what? I stand corrected. I shouldn't have been questioning people who've been in this field much longer than I have. But, that's. Huh. I usually don't consider dehydrating something like that, as in, like, drying a hydrate salt, to be a different compound. But I guess it is in this exact situation. Okay. All right, okay, so that makes sense how they're dehydrating it, and they're all right. All right, I'm mentally satisfied now. So let's see, with heat minus H2O, form this Cl. I might have to switch to a smaller brush soon. Cl, oxygen, close enough. C. N, double O, and then sodium. Yeah, we're gonna have to switch to a smaller brush next time I want to draw. Okay, but anyways, back to where we were. So they've observed problems. There's black specks, probably because of the chlorine coming off of it and starting to char the remaining bits of carbon and nitrogen inside of it. These NCl bonds are real weak. That's going to cause the chlorine to start coming off because they want to cut in half. And with chlorine generation, it's going to aggressively attack any carbon-nitrogen source it can find, especially at high temperatures. So it's burning itself alive.
But problems persisted. A sample of material taken from the dryer around 7:30 p.m. showed that moisture levels of the compound were not decreasing as expected. And now the white material contained dark specks. After Automobile texted Clearon about the issue, workers stopped the flow of steam to the dryer's jacket.
Oh, they
and
stopped
the rotation of the dryer to investigate the cause.
Oh, that's good.
Both Automobile and Clearon workers suspected that the dark specks could have been due to corrosion of 2 stainless steel valves on the dryer, which was
come on.
otherwise constructed of a corrosion-resistant material. Later, an Automobile employee told the CSB that when looking inside the dryer to investigate the suspected corrosion, the compound inside appeared lumpy with a yellowish tint and smelled like chlorine.
I wonder if it's
While the
chlorine or
workers
not.
were troubleshooting, the internal temperature of the dryer continued slowly increasing,
Oh.
even though no steam was flowing into the dryer.
Oh, so it was still reacting
That
this
is
whole time.
because,
That's not
unknown
good.
to the workers, the earlier heating of the dryer had likely caused the compound inside to start decomposing.
It's at a runaway
The dangerous
reaction.
runaway
Shit.
chemical reaction was now underway.
Didn't realize that
Workers
it's so.
continued troubleshooting.
So reactions typically require some heat to actually drive them to start, but also many reactions release heat upon completing the reaction. So if you have something that takes heat to start and then releases more heat than you put in when you did the more heat than you put in to start the reaction, then you're going to have a runaway chain reaction because the compound will keep feeding off of it the heat that other molecules that have just reacted produce, and you get this situation where now we have chlorine generation that is slowly ramping up until it's all at once, and there's a big old cloud.
And by 9:30 p.m., Optima Bell and Clearon agreed to stop the batch operation for the night and continue to investigate the cause of the black specks the following day. But at approximately 9:40 p.m., the decomposition...
It feels very weird because it just seems like they don't have like a chemistry person on site to be doing that, or on site. Like, I feel like it wouldn't take very long for like a chemist to just automatically be like, oh yeah, NCl bonds plus heat. NCl bonds plus heat is going to get you chlorine, and like that is bad.
reaction underway in the dryer increased rapidly, causing the temperature and pressure inside the dryer to spike.
Yeah,
Within
so
minutes, the dryer
that self-propagating reaction just kind of hit critical mass there with those spikes.
and pressure inside the dryer to spike. Within minutes, the dryer catastrophically exploded.
Damn.
Metal debris from the explosion struck a nearby methanol pipe, causing it to rupture.
Oh,
The released
great.
methanol ignited, and a fire broke out.
Love completely unrelated
Other metal
processes
fragments
going
from the
on at the
dryer
same
were
time.
found up to a half-mile from the site. One Optima Bell employee was killed. 2 others were evaluated for respiratory irritation, and 1 member of the public reported an injury related to the explosion. The CSB launched an investigation and found 5 safety issues contributed to the severity of the incident. They are process knowledge management, thermal hazard assessment, equipment selection and design, tolling of hazardous materials, and regulatory coverage of reactive hazards.
I already spoke on that first bullet point, because yeah, that was definitely part of the contribution to that happening, is just the people working with this material just did not really understand how this, whatever it was called, CBP or whatever, what was it called again? CDB 56, how that actually reacts to heat. Like, it is, I wouldn't say it's absolutely fundamental knowledge that NCl bonds break apart with heat for chlorine, but it tends to be, it's fairly common knowledge for anybody in organic chemistry. So not knowing that is already kind of an issue, and nobody seeming to know that on the team either. At least they stopped when they smelled chlorine, but they also didn't really do much to mitigate a possible ongoing reaction either. Yeah, thermal hazard assessment. I mean, yeah, again, kind of the whole how is heat going to actually affect this? Is it going to keep going up? Should we be concerned? Equipment selection and design. Having a pressurized reactor like this definitely feels unnecessary for what they did. Like, if they're just trying to dehydrate this, they probably could have done it in an oven. I mean, the oven would have made a horrible gas cloud, but at the very least, it would have been something they instantly, figured out. Like, yeah, it doesn't feel like the brightest idea to dehydrate things that way. Tolling of hazardous materials, so that's the whole offloading it onto someone else. yeah, not good. You usually want to be, you don't want to subcontract stuff out to people who don't know what they're doing or don't know exactly what they're working with. Then regulatory coverage of reactive hazards, well, that's too big of a body for me to know. Yeah, CL2 do equal bad. You do not want to smell that. I think I've smelled small amounts or small quantities of CL2 in my life. When in undergrad, I used to work with some, typical Clorox bleach, trying to do a reaction. The reaction really wasn't working very well, but I did make some very nasty organic hypochlorites, which have a general structure looking like this. And yeah, they definitely have the same problem of forming chlorine. I accidentally got the beaker too close to my nose once. I can't exactly remember what it smelled like, but man, it was sharp and kind of painful, pretty unpleasant, and I could not have gotten more than like just a small breath in through my nose. I had to kind of wash myself out at the sink for a couple minutes there to be like, oh my god, get this out, get this out.
The first safety issue is process knowledge management. As part of their tolling agreement, Clearon provided a technology.
Your sister was telling you about when she was in chemistry in college, someone spilled DCM, and the prof was like, it'll evaporate. For anybody watching the VOD later who doesn't know, DCM stands for dichloromethane. It's this compound. Recently regulated by the remnants of the Biden EPA from last year, and it's potentially carcinogenic. A handful of people have caught cancer and died from it. Caught cancer. I say it as if it's a disease, like the common cold. Some couple people have gotten cancer from it and died. And so someone spilled it. The prof was just like, it'll evaporate. I mean, it will. It will. I don't know. It's I have complicated feelings about the regulation, just given the fact that, like, I don't know. Unless you're like just constantly just sucking it in, I think you'll be probably okay. But I mean, it will just evaporate. If it's in like a fume hood, I wouldn't worry about it. I mean, that is also the thing, right? Like, if it's so easy to evaporate that, like, it will just kind of, by the time you clean it and sop it up with like a paper towel or something, or an absorbent, by the time that gets thrown out, it's probably so dry that it's like, oh well, it did already evaporate. It kind of is a little self-defeating there, unless you like squeegee it directly into a container and then pour that into a waste bottle. It's probably not gonna stay contained, you know? It's kind of a shame. It's hard to contain small little compounds like these guys. Yeah, it was a while ago, I figured, not, recently. I was just providing some context for anyone new. Not in a fume hood, though. Yeah, that would be maybe a bit of an issue. That at that point, it would be okay. Just kind of back out of the room, put up a fan, give the place some ventilation. Because I mean, either way, if you like stop it, like especially if it's in like a, well, I mean, it was a lab environment. Unless you have like a trash can that's gonna actually like hold in vapors, you throw that in the trash can, it's evaporating anyways. But no, it's funny chemical that is. Good story.
To assist Optima Bell in the development of the design and operating procedures for the dehydration process. But the CSB found that Clearon's technology package was inadequate and lacked critical known information on the decomposition of CDB56.
This tech package doesn't tell me the temperature.
Clearon's own safety data sheet for CDB56.
Hold up, that's a materials safety data sheet. Excuse me, CSB, it's not a safety data sheet. That is outdated as hell. That was used many years ago, and it's not standardized. We need safety data sheets. Thank you. Little point of pedantry for you all.
56, which was included in the package, listed its decomposition temperature as between 240 and 250 degrees Celsius.
They didn't read.
The CSB found that in the 1970s and 80s, a Clearon predecessor had conducted testing that showed CDB56 could decompose at much lower temperatures.
Oh, okay, so
These
they did
findings
read.
were documented in a report that
But they didn't read
Clearon had
their
in
own
its possession,
documents.
but did not provide to Optima
That's,
Bell as part of the technology package.
Okay, so the people actually contracting the synthesizers didn't tell them about the internal documentation of, actually, don't heat it this high. Well, that's piss poor management. You should actually, share some of that knowledge.
And post-incident testing of the material confirmed that CDB56 could begin a runaway decomposition at just 81 degrees Celsius.
Ooh, that's pretty low, all things considered.
Because Optimabel was not provided
That's less
this
than the
crucial
boiling point of water.
information, the company believed the drier temperatures would be low enough to avoid a runaway decomposition reaction by design.
Yeah, that's the thing, though. You gotta actually pay attention to what the data is saying. Like, I could see at this flat line that maybe they wouldn't be thinking of anything, but if, someone was still monitoring this later, it's like, oh, hey, no, it's going. Like, we've gotta shut this down.
Accurate process and product knowledge is essential for the safe operation of chemical processes. There can be little expectation of safety if the companies operating a process don't fully understand the chemicals and their associated hazards. Our investigation found that Optimabel lacked crucial information on the decomposition of CDB56. Accordingly, we found gaps in the ways that Clearon maintained and managed its key process knowledge, particularly in the way that it managed that knowledge with respect to its toller, Optimabel.
As a result, the CSB made a recommendation to Clearon to develop and implement a comprehensive process knowledge management program, or evaluate and revise existing process safety management procedures to ensure consistency with industry guidance publications.
Wait, what does that even mean in this context?
That Clearon update its CDB56 safety data sheet to more
Oh.
accurately represent the known hazards.
Basically,
of the
take their
compound.
private info and actually make it
Second
public
safety issue involved in
on,
the incident
you know,
was thermal hazard
a
assessment.
very common document.
CSB found that both Optimabel and Clearon failed to effectively assess the hazards of CDB56 and the batch operation. For example, both companies failed to identify the temperature at which the material could decompose.
Yeah, that's kind of the dirty secret about a lot of safety data sheets. So companies put out safety data sheets for their chemicals that they sell because it's good to be able to actually distribute that safety knowledge to anybody purchasing your chemical. But if you have chemistry experience and look at these things constantly, you'll start to notice they feel a little bit repetitive when you get to more complicated molecules, things that are off the beaten path, so to speak, things that aren't just used every day in industry like kilogram quantities all the time, things that are a little bit more specialty. You'll start to notice that the safety data sheets start to repeat themselves, and that's because there really isn't all that much testing going on a lot of these. They kind of just assume it's a respiratory hazard and a mild toxin and a skin irritating hazard, and then they'll be like, okay, what's its melting point? If it's a liquid, maybe we'll tell you its boiling and freezing points. Outside of that, they really don't go that in depth with what they look at, and so this little temperature decomposition thing, it's almost a miracle that the CDB56 was actually tested for this at all at some point. Now, it still seemed like it was wrong, given the temperature at which it could decompose was lower, and it caused this accident. But it just kind of goes to show that it sucks that the safety data sheets are usually the best first resource you can trust about something, and even then they don't have the greatest data on them because they aren't the requirements to actually make a safety data sheet are so minimal that you can basically you barely have to fill anything out on it, and so you don't actually give it a whole lot of useful information. It's a shame.
Failed to conduct adequate literature searches for public or internal safety data, and failed to use readily available reactive hazard screening methods to assess the reactivity.
Yeah, they could have
of the
they could have
material.
easily figured out this
Had
could make a big
Clearon or
chlorine explosion,
Optimabel
but they didn't
performed
bother.
a thorough thermal hazard assessment, the parties could have understood the hazards of the dehydration operation, and the explosion could have been prevented.
We're just gonna throw it in a
There
steel
are
drum
many
we've never used
publicly
before.
available
It's
tools
fine.
that companies can use to screen new or existing chemicals for reactivity hazards. Some of them are simple screening tools that can be used to quickly determine if further research is required. Others, like differential scanning or accelerating rate calorimetry, provide detailed quantitative lab results that can be used to design a safe process.
I know what differential scanning calorimetry is. I can yap about that for a hot second. You know what? It might take me a while. Let me put some music on while I yap about that for a hot second. And how that could actually be helpful. So, differential scanning calorimetry, or DSC, that is a technique upon which you would actually plot, goodness, what is it? It's actually been a very long time since I've thought of differential scanning calorimetry, so I may have committed to something I barely even remember. But let's see, you have time on the bottom axis, and then you would have, what was on the top axis again? I think it's the change in temperature over time, not the temperature over time, but it's change in temperature, or the amount of heat. Yes, yeah. It's the amount of heat energy being added, so the change in heat. So delta heat. And what that basically means, and let's just assume that this is, 0 for your heat value and, 0 for your time value over here. What differential scanning calorimetry does is it takes your sample that you have loaded in a small metal container. It takes that and it tries to heat it or increase its temperature at an even rate. So, let's just say, it's weird to say, but there's a constant delta in temp. And this requires heat energy to be put into the compound for it to actually, raise in temperature. You're heating it up. So usually you'll end up with a flat line most of the time because it takes a constant amount of heat to raise something by a degree of Celsius. So if your temperature ramp is, 1 degree Celsius every 5 seconds, then you're going to always be putting in the same amount of heat, some number of joules, to raise that 1 Celsius every 5 seconds. However, I guess the music's maybe a little loud for this. Let me turn that down. There you go. However, if a reaction occurs, well, remember back to what I said earlier, a reaction requires some energy to actually take off and start. So, if a reaction occurs, and let's say here, reaction start, and then we could also maybe say like this is normal heating. So if a reaction starts, well, you need energy to get that reaction going. And so your instrument, the DSC, has to start putting in more energy per second to actually maintain that temperature rise, because now not only are you just trying to increase the temperature of the solid that is, or whatever your sample is, now it also has to feed energy into the reaction that's occurring, so that way everything else still rises at the same temperature. Some molecules start reacting, the other molecules actually start raising in temperature like the experiment intended. So you can get a line that starts kind of like this, as more and more things start to react as the temperature goes up and up, and you have to start putting in more heat energy to get that reaction started. But then if you have something like this that's exothermic, it's going to start putting off heat, and it'll eventually kind of overpower the heating of the instrument. And so then it'll kind of crash down abruptly because the instrument is now trying to not put in any heat at all, because it wants to try to keep that temperature ramp constant, but the reaction is now kind of self-propagating, producing more and more heat and causing the reaction to keep going, despite the differential scanning calorimeter's intent and consent. But eventually, after that reaction kind of, wears down, stops going, positive feedback loop. It keeps going in on itself. And so Eventually, that positive feedback loop ends because there's no more reagent to react. It'll then come back up, and you'll get a flat line again as now your products of that reaction are being heated. And then, you know, usually there's like some extra math to say like, okay, well, this reaction region is going to get like the second derivative of it taken or something. Or this is already a derivative in some sense. Another derivative of it will be taken with respect to time. You'll get like a bump, and then you'll say, oh, well, there was like the area is equal to like the amount of heat that you put in, or it's like something like that. It's been a little while since I've done the exact math about this, but I know it's something like that, where it's like you determine that, oh, hey, especially at least for the point of this video, what you can see is if you do a DSC scan, you'll actually notice that there's this, you know, weird spike in the timeline, and you'll know that something happened there. Now, that something could also be, say, a phase change in which the solid is now packing itself differently, or it could be, I guess, you know, the dehydration that this company was looking for. But, you know, with careful analysis, you can actually start to determine that, okay, what kind of was the character of this reaction? Is this, you know, dehydration is usually endothermic, so you actually get a negative feedback loop. So instead of maybe a peak that kind of looks like this, you might get a peak that actually just kind of keeps going up and up and up, and then all of a sudden crashes back down really quickly once there's nothing left to dehydrate. Although usually DSCs are kind of contained little devices. DSC samples are these little contained pans, so that the water would probably stay in. But, you know, you'd still be able to see some difference in the peak with enough analysis. And so if they bothered to do that, then they might have been able to understand more about the material. I say they, probably not really the Optima Bell people running the reaction, more the, whatever the hell the other company was that's trying to actually outsource this work, because that's kind of their responsibility when they are contracting somebody. Tell them all the information about this chemical that they want made. I have a special little thing for DSC. I kind of love it in a weird sense because it was kind of the... I never used it in my research. I did one lab on it once in undergrad, but I kind of have fondness because I learned some principles of cooking because of it. Like, because you could change, like, this little, you know, delta temperature ramp as you, like, for your, for different results, basically, in the data you were getting. That's when I was starting to think about, like, oh, that's, like, why in cooking the whole meme about, you know, the classic meme of, well, if I bake this at 300 Celsius or 300 Fahrenheit for 10 minutes, then I should be able to bake it at 3000 for 1 minute. That's why that little meme joke from kids' cartoons doesn't work, because its rate of heating ends up causing this graph to look way different, and it doesn't, and just like burns everything. I actually had to start thinking of like heating rates because of this, and I'm like, oh, that's why, like, I should only use like this high on my oven to like cook my food and not go higher. Like, science, heat rates, makes total sense. Anyways, with that little diversion over.
Using these thermal and reactive hazard assessment tools and developing
Hope you learned
processes
something.
accordingly can prevent tragic accidents like the Optima Bell explosion.
In its report, the CSB recommended that Optima Bell develop and implement a written thermal and reactive hazards evaluation and management program.
They told them, stop accepting things without actually running tests on if it might blow up or not.
The third safety issue that contributed to the incident at Optima Bell is equipment selection and process design.
Also, stop using
Optima
equipment
Bell
you've never
used
used
existing
before.
Production equipment for the batch tolling operation. But the CSB learned the equipment was not designed, sized, or re-engineered for the process.
Oof.
As a result, the dryer was unable to quickly cool the contents if they became overheated, nor
Yeah,
was it able
that
to
would have
relieve
been
the pressure
important.
generated during a decomposition. And on the day of the incident, Clearon and Optima Bell essentially conducted an experiment on a new method to dehydrate CDB56 at full production scale.
Yeah,
This was done without
they didn't do the
first
bench scale
experimenting
testing
in a
first.
laboratory
Oops.
or on a smaller scale which could have alerted the company of hazards and led to changes.
Could have had a
in the
little
process.
small explosion, small
Instead,
chlorine leak.
the
Instead,
end result of this decision
this.
was a catastrophic explosion.
We found that Optimabell's pressure relief system for the dryer was not designed or evaluated to relieve the pressure produced by the decomposition of CDB56. When using existing equipment for a new process, companies need to ensure that the equipment design is appropriate for the proposed new process.
Yep.
Had pilot or lab scale studies been conducted,
Don't just shoehorn old
Optimabell
equipment you
and
have and
Clearon
assume that it'll
likely
work.
would
It's
have
not going to just be
gained
fine.
additional data on CDB56 and improved process knowledge. This might have led to changes in the equipment or process design, potentially preventing the explosion.
The fourth safety issue found by the CSB is the tolling of hazardous materials. Companies often augment in-house production by outsourcing chemical processes and other operations.
Right.
These agreements are called tolling contracts.
Yeah, they're not going
Clearon
to produce
established
everything
a
on their
tolling
own.
contract with Richmond Chemical, a tolling broker, who in turn contracted with Optimabell.
Oh, so there was a
The Center for
middleman to
Chemical
this
Process
outsourcing.
Safety, an
Great.
industry organization, provides guidance for safe and effective tolling arrangements. But the CSB found that neither Clearon nor Optimabell adequately followed that guidance. Their deficiencies
course not.
included inadequate exchange of process knowledge between the tolling parties, inadequate mutual involvement in the process hazard analysis, inadequate understanding, characterization, and analysis of the hazards of CDB56, and
It really is like the two companies that were actually meant to be involved, the one contracting and the contractee, didn't communicate directly at all about what they were doing or what they wanted out of each other in this business arrangement, and just said, hey, you know, whatever, the middleman will take care of it. It's fine. The middleman just connected us, and it's like, hey, they want you to do this job. Okay.
the dehydration operation, and no evaluation of the technology change from the type of dryer typically used for the process to the rotary dryer available at Optimabell.
Outsourcing the production of a hazardous material does not outsource the responsibility for process safety.
Oh, it does not.
Effective
Everybody
process
think that it
safety
always ends
and
once
the
you
prevention
contract
of a
somebody else.
catastrophic
Does
incident
not.
are responsibilities that should be shared by all parties involved in a tolling operation.
As a result, the CSB recommended that both Optimabell and Clearon develop and implement a written program for tolling process
So what about that
design
middleman
and
that
equipment
connected these two? Are they going to
using
get any shit? Because I
available
feel like they
industry
should get some shit for being irresponsible
Finally,
about
the fifth
relaying
safety issue that
information and
contributed
trying to,
the
like,
incident at
check things.
Optimabell is regulatory coverage of reactive hazards. CDB56 is a reactive chemical that can undergo a self-accelerating decomposition when heated. At Optimabell, the decomposition led to a catastrophic explosion, fire, toxic emissions, and the death of an employee.
Sure did.
Yet this chemical and many such reactive chemicals are not regulated under OSHA's Process Safety Management Standard
Nope.
or the EPA's Risk Management Program rule.
Nope.
Had CDB
OSHA and the
56
EPA
been
can't keep
covered
up,
under those
thanks to
regulations,
lobbying.
Optimabell would have been required to implement risk mitigation and management systems that could have prevented this incident.
The CSB has a long history of investigating reactive chemical incidents, including producing a 2002 study in which the CSB called on OSHA and the EPA to expand their standards to address reactive chemicals.
And look at
and
that.
their
Nothing
hazards.
happened in 18
To date,
years.
however, neither agency has acted on our recommendations.
Therefore, in its final report, the CSB reissued its 2002 recommendation to amend the process safety.
Feels like my
management standard
actual
to
job.
achieve more
Just feels like my actual job, just reissuing the same recommendation over and over again and hoping that somebody actually listens to me, you know, this time. It hasn't been 18 years at my job yet, but sometimes it feels like it.
comprehensive control of reactive hazards that could have catastrophic consequences. And the agency reiterated its 2002 recommendation to the EPA to revise the accidental release prevention requirements to explicitly
Real.
cover
Glad you can relate.
catastrophic reactive hazards that have the potential to seriously impact the public, including those resulting from self-reactive chemicals and combinations of
It really is
chemicals and
impossible to get people to
process-specific
operate
conditions.
safely unless you, like, I don't know,
CSB
dangle a free
believes
pizza
OSHA
party in
and the
front of them.
EPA
Then
must
they
strengthen the
aren't really
regulations
motivated
on reactive
whatsoever. It
chemicals.
sucks.
Regulations addressing reactive hazards will help
But you know,
keep
everybody's
similar
got their own
incidents from
priorities
occurring,
and problems and
prevent
shit, so
injuries, deaths, and protect
I get
those
it.
who live
I'm
in
not happy
nearby
about it, but I
communities.
get it.
The time is now for those agencies to act. Thank you for watching this CSB safety video.
For more information,
Look at
please
that
visit
carnage.
CSB.
Surprised we didn't actually get more real pictures of what happened in this. Actually, yeah. Now pointing that out, I'm surprised there weren't actually more real pictures of the scene that happened there. Usually, they toss a bunch of them in. Maybe that's all that they could learn. They could salvage out of it. Yeah, that is a pretty destroyed area right there, and that wasn't even like. I mean, what's impressive with that is that this CDB56 isn't even like a proper explosive compound. It's just it formed chlorine and it got pressurized and it got real hot and reactive. Like if this was something that would actually like want to detonate and form like proper I don't know, a proper explosion that like propagates at a very fast rate, then that would have probably caused even more damage. I bet that red building probably wouldn't even be there. But yeah, no, it's crazy what just some a big handful of hot chemicals can do. All right. Oh, video dedicated to the person who was fatally injured during this. Yep, unfortunate. Laws and regulations are written in blood, as they say. Oh, sorry to the family for their loss. Well, enough of that depressing stuff. Let's watch somebody now cause a safety disaster in sort of real time in their fucking garage. The second video we have today. Yeah, but hey, let's abolish OSHA and the EPA. Who the hell needs that, right? They're so inefficient and they cost so much money. Nobody needs those. Modern America, blood boiling, etc., etc. Well, thank God we can go and travel to Australia now and watch some guy in his shed make yellow pigment, which, I don't know, I'm interested about this one, especially because, well, one, it's a longer pattern of Tom, Extractions and I are getting into more inorganic chemistry, and two, just from a chemical interest kind of standpoint, I'm trying to think about, like, I guess I was trying to think about this as maybe a strong molecular structure at first, but thinking about it now, it's probably just more like a mix of molybdenum oxides. Why is that not writing? Oh, because the layer is off. Of a molybdenum oxide. Come on, there we go. What oxidation state would that normally have? How would that normally form? Where is that on the periodic table? It's near tungsten, right? I think something like this would be a molecular representation of molybdenum oxide, and then a yttrium oxide, which is usually like Y2O5, so something like something kind of like this. It's all kind of, oh, hold on, that's not correct either. Oh wait, nope, I know what I was trying to think of. There we go. Something more like this. It's still kind of an abstraction anyways. Most of these ionic solids are not really, they don't really look like this, but this is kind of the best way to think about maybe how their electrons are distributed. So if you actually add everything up here, you'll get the Y4MO09 that, or actually, wait, that's two Y's missing. Something like this. some shit like this. Mixing these oxides, apparently you're going to get yellow powder. So, I don't know. It's interesting. I'm interested. I think there's probably not going to be an explosion in this one, sadly. But I guess we already got one explosion for the night, so can only ask for so much. At the very least, we can expect some funny shit out of this video. So, anyways, with only a small introduction, I guess for anybody who hasn't seen Extractions&Ire before, I love this channel. It's run by PhD PhD in like physics chemistry named Tom. He's in Australia. He works out of a shed in his back of his parents' home. He's got plenty of nature area to work with, so he's got plenty of outdoor space to ruin. He usually likes making explosives and highly flammable compounds, but on his alternate channel, Extractions&Ire, which we're currently watching, he likes to make, I don't know, various other interesting things. He's been into inorganic chemistry lately and colored stuff, because inorganic chemistry makes fun colors because of the metals and how the electrons within them are arranged.
Good day, welcome back to another episode of Extractions&Ire, and today's project
fire
is to
text.
make a yellow pigment, which comes from a 2019 paper about making environmentally friendly yellow pigments. And as we have been doing recently, we're going to start from the raw materials of the periodic table.
Yeah, I like all the
So
doodles
just have
too.
samples of the metals from the periodic table, and we're going to be doing chemistry with them to...
I think a lot of the doodles that end up on his chalkboard are for like at least at one point, I think for like from like Patreon kind of like rewards, right? Like if someone's, subscribed on Patreon, gave enough money, they would actually get a doodle on the board. I think that's where a lot of them came from. And it's funny too, because I also don't think he's erased this board or at least a very large part of it in many years. So some people are really getting their money's worth out of what they put on there. In particular, my favorite is the recreation of the shitty dog that won the dog art contest over something that was actually drawn very well. But the squirrel's cute too. The grimace is a fun reference to when he tried to make McDonald's more flammable. And the lion face is also pretty cute too. I like that a lot. But anyways, what was this little thing that he's trying to do? What? Oh, are you not sure? Or do you not know about the dog? Hold on, let me see if I can't look this up. I'm going to kind of, hold on, let me close my screen on OBS real quick for a second here. Nope, not that one. Just because I think Firefox might try to dox me if I look something up. The McDonald's more flammable? Oh, that. Okay. So, no, the McDonald's more flammable is, he has, let's see, taking a quick detour here. He has a video. Is it on this channel? No, it's on his main channel. So, Explosions&Fire. He has a video which is pretty good. It's this one. How flammable can I make McDonald's? And what he basically does is that he has he takes various pieces of a McDonald's meal and is trying to chemically alter the materials to like actually make them more flammable in some way. So with and he takes different strategies for different pieces of like, say, the burger, because of like, well, the tomato's very watery, so you don't want to do anything that's like trying to dry it out too much, because that's a pain in the ass. And just dehydrating some things help make them a little bit more flammable. Dissolving other things in like, nitrating liquid is pretty good for helping that. Adding he doesn't want to just add a whole bunch of oxidizer necessarily, but he wants to chemically add like oxygen groups to kind of make things more flammable. It's an interesting video. I'll give it that. There's a lot to think about with how you actually maybe would go about such a project. I personally think he's had funnier work, but it's a very interesting video nonetheless. I encourage everybody to go and watch that in their free time. But today we're going to be watching more of this whole pigment thing. And so what was he saying earlier about the, I talked over him. He's talking about like the periodic table, I guess. Is this like a project of his now that he's like kind of used more elements?
Recently, we were going to start from the raw materials of the periodic table. So I just have samples of the metals from the periodic table, and we're going to be doing chemistry with them to try and make this yellow
Okay,
pigment.
shit. I
This
guess he's just trying to do more stuff with elemental metals. Cool.
Tantalum-doped yttrium molybdate.
Hey, there's a little tantalum in here.
Erbium-doped
You didn't tell me that
yttrium
earlier.
molybdate. And you can see why I want to do this. This is really feels like a random scatter shot of some of the most obscure elements in the periodic table. Tantalum, yttrium, molybdenum. We're going to be looking at...
You know, you didn't really used to like chemistry, but then chemists make me question my prior feelings and stuff like this for real. Yeah, I mean, it's kind of a shame where it's like most chemistry professors tend to make people not interested in chemistry, and then people who understand chemistry and like to make applications out of it tend to make it really interesting. It's like it is kind of an inherent problem with chemistry is, well, I mean, I don't know if it's necessarily a problem, but I guess in teaching it is just like the end results of chemistry are often way cooler than the knowledge of chemistry, and you don't necessarily need to know how to do chemistry to get the results. You could just freeball it and just like, I don't know. You can learn like basic pyrotechnic mixes off of the internet, and like I used to know a friend who had a brother who was really interested in like making homemade fireworks and shit, and thankfully it didn't seem like he blew his hand off at any point, but like they learned how to like get pyrotechnic mix off of like the early 2010s internet, and like, you know, they got to the fun parts of chemistry without really understanding how it worked. They just knew that it worked. And so like knowing chemistry kind of tends to make that more fun for people who are chem nerds like me, but for other people it just tends to get tedious and bogged down. And then like teaching chemistry is so much like math and heady concepts and like quantum physics in it, and it's just like, man, I just give me the explosion. Just give me the explosion. So it's tough nut to crack sometimes, but chemistry itself is fun to watch at the very least. Learn a little bit. It's kind of like, you know, even if you're not necessarily interested in going back and getting a whole chemistry degree, it's kind of like watching the History Channel. Learning little bits and pieces of history, and just for the stories of it, is also fun in and of itself. Learning little bits and pieces of chemistry to understand a small story about how somebody turns McDonald's into something you can burn is pretty good too. Exactly. Let me see the pretty colors, and that's where it all starts for a chemist. Anybody gets into chemistry, they either see explosions or they see pretty colors, and they say, "Ooh, I want to make that," and then they get bogged down with lots and lots of math. But then the math goes away after a while, so you don't have to worry about it anymore.
Why the authors would want to do that, and if this is even achievable in my home lab, which I'm not entirely sure about. But first of all, what do I
But like
make
a
this? What do I
weird
get
bootleg
out of
oven, you
making
can
a
do it.
yellow pigment? Long-time viewers of Extractions&Ire and Explosions&Fire will know that there's this big superstition around the color yellow. If we go to which Wikipedia page...
This man hates the color yellow.
Any point goes yellow, it just stops working, all right? First of all, it does go a horrible yellow color, which is never what I want to see.
Oh, there's the
Seriously,
McDonald's
the more yellow
video.
this goes, the more likely it is just to blow up at any moment. It's come up so many times across the years, but people often comment, well, if yellow is a bad sign, but you're trying to make something yellow, does it work? Am I really good at making things yellow if things naturally want to go yellow?
Right, you have to
Or
test
if
if you're
I
cursed,
actually want
Tom.
to make something yellow, will it go a different color? So today we're going to find out by making this yellow pigment. We're mainly going to be focusing on this.
That is what happens. Either the reaction goes yellow or it goes brown. Yeah, working with organic chemistry's a bitch. All my homies hate yellow. For real, though. God, like, his superstition is completely, like, based in reality. I swear to God, every time I've done organic chemistry for my research, is that if it's turning yellow, that means you've done something wrong. Something has oxidized. Something has, like, formed a weird, like, half tar in your reaction. And if you let it continue, it's going to turn brown, and that's going to be full tar, and then you're not going to be able to scrape it out and clean that piece of glassware no matter what you do. Fuck yellow chemistry. Fuck the color yellow. But anyways, let's figure out how to make a, yellow powder instead. Surely someone will appreciate that. Someone who's not a chemist. They don't know the pain that went into that.
Tantalum-based one, but if the tantalum one doesn't work, which we'll talk about in a sec, but if that doesn't work, we'll go with the terbium-based one. But these are some fun, obscure elements that I don't see.
I love the
chemistry
different word
done
art.
on all that often. So this will be good fun.
Look at that again. Hold on. One, I love the word art. I love that old crappy like Windows 95 Microsoft Word art. It's great. I don't get enough opportunities to use it, but it's my
I
favorite.
don't see
And then what
chemistry done
the
on
hell
all that
was
often.
that?
So this is a weak.
The Gmod background, the minion shirt, the 4 identical dog paws, and the yippee. Very cute. Very cute.
Good fun. So what's this 2019 paper all about? Why are people trying to make new pigments? Well, making pigments, it seems quite hard because you need a pigment to be stable both long-term, out in the...
I doubt this is going to be on screen for long. The Life Cycle of Pottery by Tom Explosions&Fire. Cool clay thing you just made. Great job, sport. Oops, fire time, because now your entire civilization burned at a volcano. Now it's a cool ceramic thing, literally. Oh no, wait, like purposeful fire time. Nice. Your pottery, mostly unfazed, gets hit by the sun's rays, all that's good. Still good enough for some rich dickhead to buy. Hooray! For the long live the Museum of London, or what is it? Long live the British Museum.
environment in the UV, you want it to stay the same color and not fade over time. But also a lot of pigments need to survive being heated to high temperatures, because if you wanted to color pottery or ceramics, often you need to do that before firing the pottery. So your pigment has to survive
Can't
getting
paint
heated
it
to
afterwards.
1100, 1200 degrees
wash
while
off.
the pottery gets fired without getting completely destroyed. So you can't use organic molecules for this, because organic dyes and that kind of thing will just absolutely burn up at those pottery temperatures. So you need to rely on inorganic dopants or inorganic materials.
Yeah,
really.
inorganic
This
pigment.
is not a particularly hard thing to do, and humanity has been coloring pottery and firing it for potentially thousands of years. It is just harder to do if you don't want to use lead. Once again, it comes up in most of my videos.
Yeah, it is. It's I'm sure he's gonna make the joke in a second, but god damn it, lead is such a useful element. Why does it have to be so toxic? It was great for like the first metalsmithing adventures that humanity ever made. So we had great plumbing. That's where we got the word of plumbing from, because plumbus used to be lead in Latin. It was good, and so it was also good for like, armor and weapons, things like that. Then it was also like, it's good for making these pigments. Lead oxide's a wonderful yellow pigment. It's very simple, abundant in even nature, in fact. It's got great uses in like it like has amazing semiconductor properties for like solar research. I'm not exactly sure why, but it just is really good at making solar cells. But the problem is that lead is so goddamn toxic and sticks around for forever that it's like we just can't use it. Lead is great, but it kills us. It's a cruel joke. It would solve so many problems if we could just use lead more often.
You can just use lead and it works really well. You get some nice yellows, some awful yellows,
Craft
vibrant
dinner
reds,
yellow.
all from lead. But if we want to do it without lead and without toxic hexavalent chromium,
like asbestos,
and maybe
exactly.
without cadmium, we don't have as many options, unfortunately.
We could build we could build the world out of lead and asbestos. It's just it wouldn't be very friendly to us. Maybe when the robots take over eventually. Like me, haha, right? Wink, wink. Maybe when the robots take over eventually, they'll build their world out of asbestos and lead, and they don't have to worry about silly things like toxicity to frail little human beings. But also, I guess, oh wow, that's a face to have paused on. Another good point he has here, though, is that like, yeah, the other compounds that typically make yellow pigments are cadmium and hexavalent chromium, which are also extremely toxic. So like, not many good alternatives there. Hence why this research paper probably was pretty important for using yttrium and molybdenum. Pretty non-toxic metals, all things considered.
So recently there's been a lot published on molybdate. So molybdenum is underneath chromium, so it has, sort of similar chemistry to chromium. They are very stable molecules. Once you get molybdenum oxide or molybdates, they can be extremely stable. And also they have very low near-infrared absorption, which is good for this concept of like cooling paints, where if you paint something in the sun and you don't want it to get so hot, if the pigment reflects a lot of that infrared light, it won't get as hot. And also you're using non-toxic elements, and that's kind of the concept.
Don't aim it downwards or you're going to fry the people on the sidewalk.
I'm not entirely sure I buy this argument too well for this particular material. Like, sure, it might be environmentally friendly once it's made, but these elements, yttrium, tantalum, terbium, take enormous amount of energies to refine, and
That's
tantalum
true.
in particular is one of the most conflict minerals or conflict.
Tin, tantalum, tungsten, and gold. All these minerals are found in our electronics and are considered conflict minerals due to their potential origin in the Democratic Republic of Congo. While the African country contains an estimated 24 trillion in untapped mineral resources, It remains mired in poverty and violence, and mining these 4 metals can help fund armed conflict in the region. Ah, yes. Great. Another reminder that our entire modern world is founded on fucking fun metals that are only found in places that are completely destabilized because of the modern world. Ain't it great?
Elements in the world, and to suggest that you can make a widespread pottery glaze that's environmentally friendly using tantalum is, I mean, it's a bit of a reach. Actually, here's an interesting thing about the economics of tantalum. So Australia has huge reserves of tantalum, and we used to do heaps of mining of tantalum pre-2008 because for some reason the stock market crash of 2008 closed all of Australia's tantalum mines.
What
But
happened in
there's still demand
2008?
for tantalum across the world. It's used very heavily in capacitors. So that demand was entirely filled out of West Africa.
Ah, yes, that problem again.
And now Australia can't open any more tantalum mines because it's not economically viable because we have to, like, compete with child slaves for some reason. I don't know how this happened. Oh, and also, one other thing I find is sort of in conflict with its environmentally friendly headline is that you need to heat this pigment up to 1400 degrees Celsius to
That's
get the
hot.
synthesis to work.
Ah, that's hot.
Industrially heating things to 1400 degrees C, very, very difficult. In fact, it's very, very difficult even on the lab scale. This paper heats it to 1400 degrees C for 6 hours. Just because it doesn't have lead in it doesn't mean it's immediately environmentally friendly. Like, come
You
on,
might have to
you gotta
burn
try a
like
little bit harder.
3,000 pounds of coal to make a gram of
In
this.
fact, when you read 1400 degrees C, you think that maybe they're just heating that because that's the maximum thing of their furnace and they don't need to go that hot. But the paper specifically shows that 1300 degrees is not hot enough and you need to go to 1400 degrees because the reaction, the solid state reaction, doesn't go to completion if it's at 1300 degrees and doesn't happen at all at 1200 degrees. A weird note is that I thought this data was from the paper and I was rereading the paper today.
Why is his own text censored? What the fuck is that?
Not in there. And then I realized that the authors had published a virtually
there we go.
identical article 3 years earlier in 2016, except using zirconium as the fucking dopant. Once again, making yellow pigments. And it is a completely separate paper. None of the data is plagiarized between the two of them, but it's blow for blow exactly an identical paper, but it's only cited in the method section as like, oh, it's used similar methods, which is like stupid. Sorry, no one's forcing me to do this work, but we got to talk about this one weird thing about this huge weird thing.
One
look
weird
at the
things
colours of the yellows,
dude,
like, with all the dopant on the end here. There's no dopant in there, and it's still yellow. In fact, it's pretty much exactly the same yellow, no matter how much tantalum or zirconium you put in there. The terbium one slightly changes color, but like you go to all this effort to put zirconium and tantalum into this molybdate.
Slightly different. Many of the 2016 ones have this kind of like light, almost grassy yellow color, while the ones here have like this kind of, this is at least how my screen is showing it. Your screen mileage may vary. Is that this 2019 one is a little bit more like a lemony, like the rind of a lemon kind of yellow. It's a little bit more full-bodied. It's more saturated. It's not as white as the 2016 pigments are. So I think there's a little bit of a difference, but I mean, within a series, no, there's not too much of a difference. Most of these 2019 ones are of tantalum, very similar. Most of these 2016 ones of zirconium, very similar. And then, okay, the terbium one does actually change quite a bit with more terbium.
It just looks exactly the same. I don't know. So
I think Tom is suffering from the whole men can't typically see many different shades of color kind of evolutionary problem, which is very interesting. I didn't know that for a long time, but it's kind of like men tend to have just fewer of like the cones in the eye that can differentiate shades of different colors. It's an interesting difference.
We will maybe make an undoped one as well and just see visually with my eyes and the camera, is the doped one actually any different yellow than the undoped one? Anyway, let's talk about the synthesis. So I've mentioned that...
Oh, I just realized that I forgot to bump the audio back up after putting the music on.
We're
Oopsie.
starting from the raw metals, so the pure metals themselves, and we need to convert them to the oxides. And once they're the oxides, this is where the paper synthesis begins, and the paper synthesis is basically mixing up the oxides.
And that's going to be a little
the
difficult.
correct
You
ratio,
have to powder
and
them
heating it
first,
to 1400
and
degrees
then
for 6
probably
hours.
dissolve them,
I very
and
recently
oxidize
bought a
them?
new furnace in a recent video, and that furnace was very good. This furnace only goes up to 1100 degrees Celsius. 1400 degrees is very hot, so we will have to get a different furnace, a second brand new furnace for this video. How do we get to the oxides? Going from yttrium metal to yttrium oxide should be relatively easy because yttrium is quite reactive. And
That's
I
good.
just have this big slab of yttrium now. And same with molybdenum. Actually, maybe not. Molybdenum is not very reactive. I think nitric
Molybdenum
acid
takes a
should
lot
be able to
more difficulty to
corrode
crack
and
it.
dissolve the molybdenum metal, and then I think it should be easy enough to get to the oxide from the dissolved molybdenate oxide species that dissolves in acidic solution. Molybdenum chemistry is a little weird, so it might get a little bit difficult. Speaking of
Not sure why it's a little
tantalum
weird,
is
but
extremely non-reactive. It doesn't get corroded by any acids really at all. Short
Yeah,
of
tantalum's a
hydrofluoric
nice
acid,
stainless
which is
steel
not
additive
something
for a
I
good
can
reason.
do in my lab. I can't do HF, so I don't really
Don't
know
handle
how we're
HF,
going
for
to
love of
dissolve
God.
some tantalum enough to get some oxides. I will try a few things. If none of that works, we will stop making the tantalum doped one, and then we will get to doing the terbium doped one.
My guess is that he's probably going to either do aqua regia to try and dissolve the tantalum, because aqua regia is good at even dissolving something as inert as gold, so that might help get at least a little bit of tantalum in solution. And ironically, I think that might be the safer option, because the other thing he's probably going to try to do if that doesn't work is boil it in sulfuric acid for a long time, which, man, you're really on a special kind of level if you're thinking, yeah, I'm gonna like boil sulfuric acid at like 300 degrees Celsius for a couple hours and see if it strips away at this metal. Like, I don't know if it might corrode the metal a little bit. It'll definitely like burn any organic thing, including your skin, if it touches you, though.
Terbium, like yttrium, is quite reactive, so it should be easy enough to get terbium oxide. But I want to do the tantalum. I want to crack tantalum open and get it reacting. Just because I have a lot of enthusiasm for this task doesn't make it any easier. It makes it slightly easier, the enthusiasm, but it's hard to bend science to your will.
But see, that's the chemist mentality that gets us into a whole heap of trouble. That's why I can understand maybe sometimes when the chemistry department is doing something unwise at my job, because it's kind of like, yeah, I understand that urge to say, you know, I don't need to do things this way, but I've got to prove the chemistry that I've got to prove to chemistry, the concept, who is the boss here, and it's me who knows the chemistry. I can control it. I can do what I need to. I'm gonna crack this thing open, even if it requires really harsh conditions, because it's fun. That's what we got into chemistry for. It's one of my favorite quotes from Tom here is so good. It is what is it? You don't get into chemistry to do math. You get into chemistry to play God. Yeah, that's exactly why I got into chemistry.
As much as I fucking try. Anyway, that's the project. So if we do this all well, we'll end up with a yellow pigment that should be yellow for all eternity. If we do it badly enough, I guess I'll burn my house down, but that's not... Why don't we start with the molybdenum? Where's my bloody molybdenum samples? Let's start with there. All right, here we have some molybdenum metal. You can see it's got that classic blue little shine on it, a bit of oxide layer. Molybdenum loves forming these blue colors, but we're not here to form blue colors. We're here to form yellow colors. So this is 30 grams of molybdenum metal. There is 17 of these pellets, just for those people who really love numbers. Yeah, very dense metal. I can't shake this too hard or I'll end up shattering the beaker. We are trying to dissolve this in nitric acid. It might react quite violently, it might not react quite violently. In fact, it might not react too much at all. Nitric acid is very oxidizing, so it'll oxidize the molybdenum, but that might form an oxide coating that sort of stops the metal from reaching the acid again. So that's passivation. If it passivates, then this starts to go very slow and can stop completely, which we don't want. Hopefully it dissolves It's probably going to fume a little bit, or quite a lot, of horrifically toxic nitrogen dioxide gas. She'll be right. Okay, let's get this dissolving.
Nothing happens. Of
All right,
course.
it's been about 10 minutes. Yeah,
Something
we're definitely
happened.
getting corrosion of the metal. Not at a very high rate, though. And there is a lot of nitric acid there. So I've seen some reports Aqua Regia does react very fast. With
Oh, cool. He's going for the Aqua Regia immediately. Tom, the nitric acid is working. You just maybe should add a little more. Maybe get stirred around a little bit. Like, come on. The burnt hot plate. I know this hot plate has been through so much abuse. So much abuse. I mean, I think last video this when he poured a whole bunch of bromine on it by accident. So yeah, this poor hot plate has really seen better days. I'm shocked it's still working. Hot plates usually, you know, shit out for less, but this one was made good, built different. Accident. Yeah. I mean, you know, not thinking things through is considered an accident, right?
molybdenum, so Aqua Regia is a combination of nitric and hydrochloric, which is usually used to dissolve gold. This will help. I think that powder in there is what we want. Once we dry it out, it should be molybdenum trioxide. It's kind of a bit hard to work out exactly the chemistry of all this, but I think once we add a little bit of hydrochloric, it's also going to dilute it a little bit, give it a bit more water, which may help with initially dissolving this oxide layer and keep this stuff reacting, because the hydrochloric acid here is only about 25%, whereas this nitric is 70%. Let's give that a shot. See if it picks up reaction speed a little. Oh yeah, it's bubbling.
So Aqua Regia is so powerful because it makes, I think... Actually, wait, that's not quite the species. I think that's the species, this HNOCl stuff.
Ooh,
Really unstable, very reactive, and aggressive adder of this H+ to a reaction mix. So, yeah, that's why this is making this go even faster than either of the two acids could do on their own. Yeah, look at all that delicious brown gas. Good for your lungs. Does he have a fume hood? Is just raw dogging the chemistry in his garage? He definitely doesn't have a fume hood. I think his typical setup here is this is like kind of garage door open, fan on, wearing gas mask kind of deal. So directing the fumes away from him, but certainly right out into the open atmosphere. And if the winds change, that's not a good sign. Amateur chemists really get away with murder. Their safety practices are abysmal, but I mean that's because good safety is expensive. I hope the mailman isn't coming. Yeah, true. I hope.
Okay.
I hope there's no wildlife, you know,
red,
also going and getting poisoned.
It went yellow, and then I kept heating it, and now it's blue. I mean, this happened over the course of about a week and a half. The molybdenum is mostly dissolved. I've been adding a little bit of acid.
Wow, a week and a half took that reaction to complete. It was reacting so vigorously that whole time. The metal still took a long time to break down. It took a week and a half. That's wild.
Over the course of the week and a half, just try and get it dissolved. It dissolves very slowly. It looks like it's dissolving fast when you put a lot of nitric acid in, but I think the nitric acid is maybe just decomposing or getting catalytically decomposed because it puts out heaps of nitrogen dioxide gas.
You'll see the steam coming off of it.
Unsightly amount of nitrogen dioxide gas.
He's trying to boil it off.
The metal doesn't dissolve in that process. I don't know why it's blue. This is actually a very typical molybdenum blue, actually. Known for this blue color. I don't know. We're trying to make molybdenum trioxide. This is what we think is in here. It's kind of why it's all sludgy. Wikipedia lists it as a yellow solid that sometimes appears blue and green. And maybe that's what we've done here. We've made our yellow solid appear blue. That's not a great sign in our project to make something yellow.
Can't turn things yellow when he's trying.
The first thing we're trying to make that's yellow goes a vibrant blue. We'll see how we go. Molybdenum trioxide is reasonably soluble at...
I mean, hey, it's definitely a molybdenum color. It's some ionic state of molybdenum, so kind of on the right track.
This nice powder that we can filter off and collect. I don't know what color it's going to be once it cools down and the solid. Could be this blue, could be green, could be a brand new color. One interesting thing is that first red color, that brick red color, I don't know what that is, and I'm not entirely convinced that anyone knows what that is. There was a post on Science Madness a couple of years ago where people were like, what's up with this red color when you put molybdenum in concentrated nitric acid? And no one could find any references to it. And you look online and people just say, yes, it dissolves to form molybdic acid, which is clear. So no idea why it goes red. It's some complex, some unknown complex that no one's figured out. Probably no one's tried. You know, you go down the...
I have to imagine maybe it's just a very low oxidation state of molybdenum. I don't think I really have the time to fully explain this, but usually as you go from low oxidation states of molybdenum or of a metal, so if we go say like, I don't know, MO2 plus, let's say, and then as the oxidation state goes higher, that means it's kind of lost more electrons. So you can say like MO plus 3, MO plus 4, MO plus 5, MO plus 6. That's a terrible plus 6. Let me redraw that. Plus 6. There we go. That would be saying like higher oxidation state. And it means that in whatever form the molybdenum is actually taking in solution, it is losing more electrons in its core, in its nucleus. And for reasons I can't entirely get into, this will take forever, and we have a lot of video left to get through. This causes color to change because the electron structure changes as you take away certain ones, and the molecule kind of reforms a resting state. And well, if we're going for something that's probably like the molybdenum plus 6, that might be like a kind of bluish color, then from the red, that would mean that we're absorbing a wide bandwidth of light, so something kind of in like the UV to green territory. As we move towards the right, we're absorbing smaller bandwidths of light, absorbing like red-orange territory, so I would guess maybe it's just some unstable molybdenum 2 or maybe a molybdenum 1 species. I don't know. Not too sure. But it also is good at evidence that if you hit it with more oxidizer, like hydrogen peroxide, then it would take away more electrons because it is an oxidizer. It increases the molybdenum's oxidation state. And then you would start getting the more typical compounds, the molybdenum 4s, the 5s, the 6s. So... yeah, no, it's interesting if no one's ever actually bothered to isolate that at all.
Periodic table to some of these slightly more obscure metals, and it's so easy to hit chemistry where people are like, oh, I don't know, it just goes red. Like, what do you mean? Like, there's probably some complex, but no one knows what that complex is.
Probably something.
Let's get this
get a
down
basic paper out of it. No one's gonna do that. Where's the funding in it, after all? Living in water, no solids at all. And Tom, I'm surprised you're not just going for the easy method. Like, you just add base to it, it'll probably crash out. Oh, okay, I guess you got the nitric acid to work. I don't know why that works, but not the hydrochloric. That's weird. Even I am unsure. Although, so this is the thing. This is a brown color I'm much more familiar with for molybdenum. I think molybdenum is often like one of the metals that's like common as a catalyst of some kind in organic chemistry. Yeah, and so you kind of get this doo-doo water. Oh, but now it's green again.
Sort of oxide.
Oh, how weird.
Bluey green. We have this deep red liquid and 2.8 grams of leftover metal. So, there's what, 27 grams or so of molybdenum dissolved in here. I mean, it looks like a couple of grams of oxide.
Even after a week and a half, all that metal didn't actually react.
All our molybdenum is
still some
dissolved.
left.
Well, most of our molybdenum is still dissolved. We'll collect this, but then we still need to think about how we get this molybdenum out of solution as this molybdenum trioxide. Maybe I'll just boil it. Why don't I boil it? It seems to choose a different color every time I heat it up.
Why didn't you boil it?
So why don't I just boil it again? Maybe it's going to go yellow or blue or green.
And if you get rid of all the water and all the acid byproducts as gases, you're gonna just be left over with the metal.
What's going on? Where's all the solid? Okay, maybe it's too concentrated. Maybe there's too much acid. Maybe the chloride is complexing the molybdenum and that's keeping it soluble even though it's at a low pH. I'm going to try just some sodium hydroxide in water. I'm going to add a tiny bit of this to the sodium hydroxide.
Adding the base.
See if anything precipitates out.
Yep,
I just
good idea.
Be careful here because it's a reasonably hot solution.
I mean, I guess you could get molybdenum hydroxides, but you heat up molybdenum hydroxides, those will just go ahead and form, an oxide eventually. I got to crash out as a blue color. That's nice. That's something.
Okay, we had something for a moment there. So maybe if I balance the pH just right. I don't know, I'm obviously just making this up now as I go, but...
You could also see the chemistry, fuck math kind of mentality coming into play here.
Oh, no, maybe it's coming back.
It's not bothering to actually do math, but how much base should I have? How should I calculate this? Get to the actual calculation. Just pour it in. It'll be fine.
Alright, now it's too acidic again, I guess. Alright. Hell yeah.
Look at that.
Okay,
Perfect
what
amount.
happens now if I add in a splash of nitric acid?
Now he's just in the
Yellow,
fuck
right?
around
That's the thing I
phase.
want, right?
Yay, play around with the acids and bases.
Oh, wow.
Whoa.
Oh
Huh.
my god.
What the?
What a colour change. I'm the master of yellow. Alright. God damn, this is vibe-based chemistry, but... my goodness.
It was
Wasn't
a
that
pretty blue,
transition?
and now it's tan. Huh. I gotta say, even I guess I'm not super familiar with inorganic chemistry as much as I thought I was. Oh, now it's blue again.
Heating to get it dry, and
Oh, look at that.
on some mild
Turning
heat,
yellow.
it's losing its blue.
Oh, God. This is a complicated one. I've kind of lost track of what's going on. My guess maybe here is that...
So I've got some of that...
My guess maybe is that the, like, molybdenum hydrate... Oh, I'm drawing on multiple layers. Ew. Is that maybe, like, the... Yeah, the molybdenum hydrate, like, you have, like, this molybdenum oxide that's forming, but it might be crystallizing out with, like, some number of water molecules. And maybe this is blue? And maybe in solution as well, because it's surrounded by so much water, it's blue. But then with like enough heat, you drive off the water. And then you form the yellow molybdenum oxide. Although I don't know what's going on with like all the filtering and turning green sometimes, and then, you know, getting all this. I can maybe think of why the solution turned yellow when nitric acid was added. Maybe whatever like molybdenum bonded to like some number of water. Hold on, let me draw that a little better. Molybdenum bonded to some number of water molecules kind of gets displaced when you have NO3 ions in solution, and those will displace the water. And then you get like some mixture of like water and NO3 coordinated to this, and like maybe this is green. Because you could be like changing out the things that are bound into the metal also changes that metal's structure of its electrons, and that'll shift around energy levels and the orbitals and what wavelength of light it absorbs, and therefore what wavelength of light it looks like. And so maybe the nitrate has the strength to bond like this, where maybe like the chlorines or the hydroxides don't necessarily. There would be a hell of a lot to think of with this. It's intriguing. I would need like an actual day to like sit down and think about this and like look at every little thing happening. But that's cool as hell. That's why inorganic chemistry is awesome.
Sold it off, filtered off, but the stuff that came through was still brightly coloured, so I'm certain there's still molybdenum in there, and I've been
still got
trying
that
to
molybdenum red
pH
again.
balance it so we get the most precipitation, because if we go too acidic, all the precipitate seems to redissolve, and too basic, it redissolves again. So if we hit just the right pH, lots of solid starts coming out, and I don't really know what pH that is, so I'm not really sure what I was optimizing for, but just balancing additions of sodium hydroxide solution with nitric acid solution. Anyway, all this to say, I think I'm right on the verge. I'm just slightly too basic, so...
Just slightly too basic. That's what they said about me in high school. Ha!
Ah! Slightly too basic, you know? Yes. Solid.
It looks like a strawberry drink.
Oh, yeah.
Now something different.
Fantastic. Okay, I cooled it down as well, because I think it's got reasonable solubility in water. Here we go. This is what we want. Once again, a different colour. It's done every colour so far. Actually, you know what? For the sake of it, why don't we see if we can get nice crystals? Now we know we're at the right spot. Let's heat it up and then cool it back down and see if the stuff dissolves.
Oh,
and then,
Tom,
precipitates
flying
out
too close to the sun
reasonably
once
nice
again.
crystals.
I've
Although
been in that
this
position
sounds
too.
fine, but, you know, let's see if
Letting
it
your
looks
ego see if
nicer.
you can't get
I
something
don't
really
know.
nice when
Might
you
be
had
cool.
something good enough.
Next day.
See a couple of pockets of crystals forming on the side. A lot of otherwise little small crystal lights that have formed and crashed out. Ooh, no, those are really nice. Look at those lumps. Those are beautiful. They're like little geodes.
Okay, and after all this, we ended up with 3 batches of molybdenum trioxide. Well, supposedly molybdenum trioxide. We have this first batch that we filtered off that was sort of white, and then after filtering was green. We had this batch which couldn't make up its mind. It was blue, and then it was a white suspension, and then on cooling it's sort of turned back a little bit blue, and so the yellow and the blue really makes it a bit of a green colour. In the end of it, this second batch really looks like the first batch. I'm fairly confident that this is molybdenum trioxide. This third batch, the batch that we just tried to recrystallise, looks quite nice, apart from the fact that it's bright pink.
Red.
Or really orange. Some extra crystals down the bottom here. I don't know, I don't really get this. I'm not entirely convinced that this
I
is
get the
molybdenum
feeling that if he
trioxide,
just
although
dries
I
it
don't really know what it is,
all
even though
completely
that
down,
batch should
just
have been
leaves it in the
purest
air
and
for a
the
while,
one that we
it will
spend
all
the
be the
most
same
effort on.
color at the very least.
I like this stuff, so maybe I'll stick with this second batch here. That is okay. I'm okay with this. Given this one, I thought it might have got a bit complicated, this molybdenum chemistry, and I was correct. But let's move on.
And
to
again,
something
too, that would
maybe
actually
a bit
support
more
the
simple.
idea
I'm
that,
not
like,
gonna
maybe if
say that
it's
going to be simple, because it never is.
maybe if the blue is a hydrate, then it's just absorbing water from the dense Australian humid summer while it sits out. That's why it's no longer yellow.
Anyway, the yttrium. Let's go dissolve up some yttrium. All right, are you ready to see the yttrium slab? Are you ready? You think you're ready? Hell yeah.
Little square or cube of yttrium.
It's pretty good,
Nice.
but maybe I shouldn't have hyped it up so much. This is, what's it say? 126 grams of yttrium. It is a dense, rather uninteresting block, but yes, a rare earth. We don't need 126 grams of metal for this reaction.
Are you sure?
We might as well do a reasonable amount of it. I don't know, maybe
Yeah.
half. How are we going to
Chilling in a sandwich baggie. Probably sent to him from some guy halfway across the world on eBay.
Carefully break this up.
Carefully breaking it. It's taking the Nile Red approach and is just damaging everything else instead of the fucking metal block.
On second thoughts, breaking it is a stupid idea. Let's not do that. Let's get our big block into the water, and then we'll add some hydrochloric acid.
Now hit it with a
and
hammer.
that will start dissolving it away. Let's go.
Alright, more of a simple, conventional metal dissolution. Yttrium being much more reactive.
Look at me slab. Beautiful stuff. There we have. There's a lot of hydrogen though, so no one light any cigarettes nearby, okay? Just gonna let
No,
this
it's okay,
hydrogen
Tom. I won't.
run away into space. All right, it's been reacting for several hours and I've been topping it up with acid. Whenever it starts to really slow down like it is now, I don't know, maybe it reaches a solubility limit. Maybe when the acid runs out, the water still reacts with the surface, but slowly, and it starts to form a bit of a hydroxide layer over the metal, which sort of protects it and slows down the reaction rate. I don't know why it's so grey though. We saw this before.
Block, why not hit with hammer? He really should have went with the
Maybe it
pickaxe.
was the ytterbium that we dissolved, and it really went very grey. So I'm not quite sure what all this grey is, but it's not going crazy.
It's probably just suspended like metal powder, Tom. You did probably make a good bit of metal powder on the surfaces, and if it's cooling down, maybe it's starting to come back out.
So it's enough
It's
to
reoxidizing with the air, maybe.
overnight. And we'll come back to this maybe in a couple of days. If it was a bit more reactive, I couldn't leave it like this, because as it reacts, it gets hot, and then the heat makes it react faster, and then it's going, and it takes away. But this
Yttrium blocky.
I'm not concerned about it getting too hot. In fact, it's cooled down. Now it's not going to get any hotter, and the reaction should taper off at some point. I don't think there's enough water and acid to dissolve this huge whole block. In fact, our slab's still mostly there. There's heaps of it there, so I don't know what will stop this reaction, but
I would laugh my ass off if it comes back the next day and it's completely gone.
Okay, day 2 slab update. Slab is still there. Yeah,
Thankfully,
there's a lot of debris in this flask. Is that a good word for it? What is all this stuff? Oh, who knows? Anyway, lots of slab, so I think worthwhile we add a little bit more acid and keep it cooking. Maybe give it some heat as well. Just get it restarted. Get it cooking, Subscribe for more slab updates. 1 week slab update. There's still a lot of slab. I don't know, does the slab look smaller a bit today?
Weak translation.
Maybe.
He forgot to check on it.
I think there's probably enough yttrium dissolved for this project. But once again, there's still so much of this crap down the bottom. So
Seems
what I
looking
might
weird
do
now. It's like
is,
covered
even
in
though
like a white
most
coating.
of this stuff is what we want, I might re-acidify it and then filter it off, so anything that doesn't dissolve in acidic solution, like this grey stuff.
Yeah, this is
Oxide
unusual
or
as all
some
hell.
sort of parts of the metal that sort of have fallen off but haven't reacted with
Unclean
the
glassware,
acid somehow.
unclean metal.
Yeah, I'm going to re-acidify it and then filter all this crap off, and then add sodium
the block
carbonate
said it was
to,
99.9%
precipitate
pure,
out the
but
yttrium as
not
a
sure if that was a
solid. The
reliable
yttrium
source or
carbonate,
not.
which, we can use
Might be
directly
other
pretty
stuff
much
in there,
as
other
a
metals.
stand-in for yttrium oxide, because it's just going to decompose into yttrium oxide under the strong heat conditions that it's going to be in. So we can precipitate out hydroxide or carbonate or anything that will easily decompose into the oxide. I'll probably go carbonate just because it tends to make solutions that are easier to filter. Bigger particles than oxide sometimes gets very sludgy, and it's like filtering paint. We can
Oh
filter
yes,
off this
definitely. I
greyness.
totally relate.
Greyness. Just horrible grey stuff.
Yeah, what the fuck is wrong with his block, dude? I mean, unless it's maybe it's found, like, I don't know, basic particles out of the air. Maybe that's forming the hydroxides or oxides. Maybe those are insoluble. Maybe it's not that acidic anymore. I don't know.
All that just for 26 grams dissolved.
Oh god. That yttrium block is probably not good anymore. That looks corroded all the way through. Like it looks like it's a porous metal. Probably has damage inside now. Ooh, slop, just like what I'm making. Nice.
Beautiful.
Sodium carbonate, and then look, wee, little snow comes out. Ain't that beautiful? Oh, hell yeah. It's clogged. We love clogging beakers with basic pastes. Well, at least this one's going a lot simpler than the molybdenum chemistry.
Dry yttrium carbonate. Looks like
I mean,
quite a bit there.
makes sense that's going a little easier. Yttrium only really likes the 3+ oxidation state. Molybdenum likes a billion different ones, so...
Grams or so of the block dissolved. That's fine. This is great. We can go on to the next step, which is the tantalum. And I still, despite doing all this, haven't really thought about...
Oh yeah, we get to watch the good one. The one that we really don't know if it's going to work at all.
I have maybe concentrated sulfuric acid. If we reflux it, get it at 300 degrees and do that for many hours.
And what did I just say? Or what did I say at the beginning of this video? He's going to fucking boil the tantalum in hot sulfuric acid for several hours. Oh my god. Alright. About to witness a great safety hazard.
Maybe we'll dissolve a little bit of it. Maybe we'll heat it and put chlorine gas over it and try and distill off.
Chlorine gas? Oh my god.
Tantalum pentachloride. That sounds difficult.
God.
Yeah, I'll think about it.
He's really dedicated to the bit.
I have an idea. Okay, I've got it, I think. One of the few things you can't use tantalum crucibles for is molten hydroxide. So people make tantalum crucibles because they're very inert and you can take
We
them
do
high
love the
temperatures
dedication,
and they won't react
but...
with pretty much anything.
Oh my god.
They specifically say that you can't use molten hydroxide. So if we react molten potassium hydroxide, one of the most corrosive substances known, with this tantalum powder, it will dissolve, hopefully. Well, it'll form some sort of potassium tantalate, which we can dissolve in hot water or dissolve in normal water, cold water if we want to, and then add some acid, and then that should precipitate out our tantalum pentoxide. That's the hope, obviously. If we've got an incredibly corrosive substance, what container do you put it in? Because molten hydroxide will eat through glass and ceramic. I've got some stainless steel here. This is obviously not a crucible, but, you know, anything's a crucible if you're poor enough. Oh, I've just put this down, ants. It's gonna be really hot. Oh, all right, I should move this. I feel bad for the ants. Will the molten hydroxide eat through the stainless steel? Yes, absolutely. And it'll form chromium and iron oxides. I think the nickel might be okay, but it's kind of a rare exception. But yes, we will have to chemically then separate the tantalum from the iron and chromium, but hopefully that shouldn't be too difficult, as both those
those ants are about to become...
solution, and the tantalum should
those ants are about to become part of a fucking mixture. Like the hell that they don't know.
Before we eat through the steel and leave the container. So that's the hope. Can we react the tantalum quick enough before we eat through the
Why doesn't he just get a fucking table? Why is it on the grass? I mean, I guess he doesn't want the whole thing to burn down.
150 or so, which is...
It's not going to be God to the ants. It's going to be the devil. Like, I guess I should, like, elaborate on what he's saying. So he's saying he's going to use molten potassium hydroxide. He is not kidding when that is one of the most corrosive things you could think of. Like, potassium hydroxide, extremely corrosive base when dissolved on its own. I mean, it's forming the pure, like, basic ion of hydroxide in solution. It's forming OH minus, which that's just what happens when you deprotonate water with a base. He's not making a solution of it. He is making liquid potassium hydroxide. That has a melting point somewhere in the range of 300, 400 Celsius. He is going to make liquid hell to react with this tantalum. That is fucked to try doing at home. I understand the dedication this man wants to commit. That's too much dedication. I don't think this is a good idea. This is a bad idea. And everybody's here now in time to see the bad idea that's about to happen. Welcome, Grim and D. You're about to watch a man probably melt a fucking pot in the attempt to try to dissolve tantalum metal. This is not something he needs to do for the project, but it's something that he wants to do, which I can understand as a chemist. Wanting to do something is sometimes more important than actually doing it. But this This is genuinely stupid. I'm glad you audibly snorted for that. From someone playing X6 to another bad idea. Yeah, at least X6 can only harm you mentally, though. This could go bad. This could go real bad.
Should cool down quickly so we don't.
Also, there's ants everywhere because he doesn't want to put it on a fucking table. Because he doesn't want to like end up boiling the hot plate.
No.
And then boiling whatever he mounts it on either. X6 can't dissolve human flesh. It can make you tear your face off.
Cutting that one out? I think we cut that one out.
Okay. Let's see how this goes. At the very least, he has the tantalum powder, so he doesn't have to run this for hours to try to eat through a block of tantalum. A random amount of KOH based on vibes. Oh, hell yeah. Make a kaiju ant. No, it's not radiation. He's just gonna melt the ant into a lump of organic flesh, and then it's going to turn into fucking ant gas.
On the Barbie. No, I can't do the Australian accent.
You can't do the Australian accent, says most Australian man in the world. Beginning to think this dude might be a mad scientist. You think? Maybe? It's fucking producing Look, okay, that's another thing too. It can produce hydrogen gas in slight quantities as well.
Hydrogen? Seems like hydrogen.
It's probably the fucking... I don't know what metal he's using. It's clearly a little bit more... Oh, I think he said stainless steel. That's a little bit more corrosion resistant, but, like... That's still going to, like, react out a surface layer. And if you react hot enough base with most metals, you're going to actually start forming, like, metal oxides and then hydrogen gas, which is very flammable. This is fucked. You better not be huffing ant gas. Huffing ant gas who can't hang. That's true. I guess he is proving how cool he is, and I'm proving how lame I am for not having a supply of ant gas on hand at all times. But I guess, I don't know. I just thought that vaping wasn't cool, but I guess if you're smoking that ant pack, then things are okay, I suppose. Wouldn't cook with that pot afterwards? Yeah, I don't know. That pot's gonna be through absolute hell. I am very interested in just seeing what the fucking pot looks like after this.
Back up even more. You're on your own camera.
Oh, there's probably gonna be another hydrogen explosion. You could... Oh, okay. Oh, hey, look at that. Look what I said. You can see that there's green creeping up on the pot. That's because the molten hydroxide is eating away at the metal and forming metal oxide complexes. That's probably the chromium portion of stainless steel that is turning multiple different kinds of colors because it is now oxidizing. Some of the brown, that's the iron part of stainless steel. That's probably iron oxide, good old rust. I think this thing might fucking melt and before he actually gets a chance to toss tantalum in there. This is gonna be great. All the cool kids smoke vape ant gas, true. He's retreated at this point. He has to still throw the tantalum in there eventually. This is a terrible idea.
I'm gonna quick wire my head here rather than let it eat through the container. You can see that green from all the chromium. What do we think?
Oh, he's stopping. Good.
It's safe to approach.
Fucking bastard. Sand the steel pot. Yeah, don't worry about it. It'll be totally fine. Oh, he's just neutralizing it a little bit with some fucking acid. Great.
It's been like half an hour.
Astroman 3 OST, true. He does have kind of that vibe and a half type playlist.
Milky. new alternative milk, this one. Alright, let's
Alternative milk. Okay.
Alright, this is our solution. Look, we made a yellow. It looks like we have our tantalum pentoxide maybe already suspended in the soluble tantalum species. It might just decompose.
Oh, he did have the tantalum in there already. Okay,
yellow
good.
And orange a bit, so it's probably the iron and chromium, especially even chromium, causing this yellow color.
It's got other metals in there.
So we'll acidify it. Hopefully everything, all the ions that we don't want go into solution. Obviously, the chromate is
I
In
would never
solution is
drink
a
that no matter
cell
how
accentuated,
much
but
money
we're
you
gonna have
gave
to add a
me.
lot of acid actually. So
That's
got
like
nitric acid here.
that's not just death. That's painful death. That is agonizing. Everything is all your organs are melting kind of death from the inside.
There's a lot of potassium in here.
Yeah, that table's seen a lot of shit.
Can't just add it in all at once.
Explosions,
That'd
fire,
be very bad.
paint
So,
strippers.
slow additions.
Yeah, I agree with Grim. I would pay you money to not drink that. Do it for the meme, though. That's the fucking, like, last meme you'll ever make. Well, at the very least, I guess this worked out for him. He didn't blow himself up, and I suppose he has some tantalum. Maybe. I mean, probably mixed with a whole bunch of chromium. Now, how is he gonna separate out the metals? He should have just tried the refluxing and sulfuric acid.
Hours to filter. It's like filtering.
That would have been
paint.
easier. It's
Something
safer.
We were trying to avoid with the yttrium one, but we could not avoid it here with the tantalum pentoxide. It is not a nice white powder. It's a bit greeny grey. The fact that it was yellow.
The corrosive waste challenge. All right, that's fucking great,
B.
B. Thanks.
A low amount of chromium.
I will think of that now at work.
I'd love to fix this. I washed it quite a bit to try and get the color out. The chromium contamination, I feel, has the biggest potential to cause a shift in the color of the end product, because a small amount of chromium can really change colors as a dopant. But you know, we'll press onwards. Maybe this is just how the tantalum.
No, the corrosive waste is a great name for it. Trust me. I mean, you're right. You're definitely right.
Bit of unreacted tantalum powder from that reaction mix.
Weird mix of tantalum, chromium, hydroxide, potassium.
There wasn't really much mixing in that reaction apart from all the hydrogen generation, which was a little bit scary. But yeah, because the tantalum metal is so heavy, I could just decant off the oxide and leave behind that tantalum metal. So hopefully there's not too much metal powder in our final product of the
Something
oxide.
plastic
But,
explosives
I'm
challenge is
fairly
probably actually
confident that
safer,
they're
honestly.
really
Most
will
plastic
be
explosives
pretty
only a
minimal
secondary
stuff.
explosive.
Yeah,
You have to have
it
something
really
else
looked like it
detonated
reacted
to
completion
propagate
as
the
long as it
explosion,
had contact
start it
with the,
off.
Potassium hydroxide, so I really should have mixed it better before heating it, but it's good to see.
I would still recommend not eating it, but you know.
We have the tantalum pentoxide right now, so we actually have all our ingredients. We've got our yttrium carbonate, we've got our molybdenum trioxide, and our tantalum pentoxide. So we can get to the step I've been stressed about the most, which is how do we heat this whole mixture? Once we mix it all and grind it all together, how do we heat it to 1400 degrees? Let's
Oh yeah,
go.
let's go to 1400 Celsius.
Okay, finally.
Which, for anybody who remembers,
so I've got this.
anybody who remembers the previous videos I've reacted to from him, he had recently purchased a furnace that went up to 1100 Celsius. Won't go up to 1400. He had to buy a whole nother bootleg ass furnace for this project. Very good use of his money.
Cool box here. This is, I'm going to call it my old furnace. I got this somewhat recently and have used it once or twice. Worked well for that video. Just won't get hot enough for what we need. Let's get this bad boy out. I've sort of just opened the box and that's all I've done. So
Oh boy.
what's in here?
What hell
What did I
machine has
buy?
he
You know,
purchased?
that's one of life's greatest joys is buying shit for yourself and then forgetting about it and then being like, wow, I know myself so well.
Being
Let's
I bought
go.
this 6
What do we
months ago
got?
for a video I started back then.
Stuff and other things. I gotta get this out of the box. I can't talk while unpacking things. So let's get it out of the box. Here he is. Here's this bad boy. Look at him. He is an induction furnace. So
Pieces
this
of wood
standard
to get
type
it
of metal
started.
melting furnace over there will use resistive wires. So you've got this wire.
When mad
that
scientists
you
get
put
a
current
bootleg
through and the wire
1400
gets hot
Celsius
and then-
furnace. Actually, you say that. Most research labs will get a bootleg 1400 Celsius furnace because it costs probably 60% of what a good 1400 Celsius furnace from like a reliable company would sell it for. So instead, let's just go ahead and buy it from fucking, likely China and just get dog shit, and it's like very cheap. It's great. Unrelated, you like the shape of the masonry puzzle pieces, tile guys. Good chat interaction. I'm happy about that one. Anyway, stop it. You haven't eaten in 8.5 hours? Oh my god, yeah, go eat, Grim. Have a good night, dude. Thanks for showing up.
makes
or even
the
a little bit.
crucible hot. But if you want to go to high temperatures, you're above the melting point of the resistive wire a lot of the time. So instead, you've got to use magnets and induction. So this is what this one is, and this is why it has the higher temperature, higher maximum temperature, and why it looks a little bit more technical. Shout out to this one Nile Red short where I saw him melting steel.
That's where he purchased it. All right, well, at least he knows it won't blow up.
Attention, do not left the heated liquid metal cooling in the graphite crucible. That seems important, but I'm not quite gathering what it means. Okay. Maybe I do have to read.
I was gonna draw a diagram to explain it, but we're already kind of low on time.
Graphite crucible with metal.
But basically, what an induction furnace like this is gonna do is that it's going to actually create magnetic currents back and forth within whatever is actually in the center of that furnace, and that's going to cause it to heat up, and it's going to be much more energy efficient than just like a heating element, and you can get to these high-ass temperatures because metals are magnetic.
So there's this water cooling line. Okay, yeah, so this is a chiller unit, so we'll keep the water at a nice constant temperature.
Yeah, you're about to see an induction furnace in action. It's a beautiful thing.
I guess you've just got 2 buckets of water, and it pumps cold to hot, and then your bucket will eventually run out. So you need to keep refilling the bucket. Okay, this is good. I'm learning things that will prevent my house from burning down. This is good. Speaking of my house burning down, I was going to turn this on right now, but this is a 16 amp plug. That's a lot of amps. I don't think I can plug that into the shed area without immediately blowing the circuits. So
okay, so where are you going to plug it in?
Consideration, I guess. All right. We've made great progress. I
hope you don't plug it in inside your home.
Before I can turn this on. All right, let's get somewhat more organized. I forgot. This higher amp circuit has a slightly different plug than your normal extension cord, so you can't actually plug them into each other. Yeah, see, it's the same shape, but the actual earth pin is bigger. So you actually need a different outlet. 15 amp or a
thought he said earth penis.
16 amp.
Immature.
50 volt. That's a bit weird. Let's go get a 15 amp fucking circuit. All right, just go buy more things for this. Why not? I have bought this thing, which is an adapter. Well, I don't really get the point of this. It's just making a 15 amp socket, which, like, I get, but you can still only draw 10 amps from it. Like, this was $70, and you're telling me that all it's doing is changing the plug shape, really? Isn't it just a
still not the amperage you need either, Tom.
Why would this be a product that exists, and why did I buy it? Let's just see if it immediately trips the power or like the cables catch on fire or something. At least if it starts.
Yeah, I mean that makes sense for lab experience there, D. I mean, I don't think I remember hearing your full lab experience. I don't know. I think I vaguely do. It's probably during one of the Mega Man X streams, I think. But yeah, thankfully acids don't work like they do in the movies. Unless they're boiling hot, they do tend to take a little bit to corrode your skin. Unless you're working with hydrofluoric acid, in which case, well, you're probably poisoned already, so yay!
I don't think it's going to do any heating without, like, tripping the circuit. But then how do I power it? Anyway, let's see if this thing turns on. This plug doesn't even fit in the fucking... Alright, that's
yeah. Fatigue like that is really, really makes labs more hazardous. It's a shame that they're so inflexible about scheduling. It really makes for a pretty bad hazard, all things considered. I mean, I had, my graduate school had undergrad labs that started at like 8 in the morning, and then, you know, they lasted for like 4 hours each, and there was like labs that also started as late as like 6:30 p.m., and it's like, what? Well, okay, no, it didn't last for 4 hours, it lasted for 2 hours, but still, it's like, oh my god, the turnover on that was insane, and had the inflexibility because you were assigned like one specific time slot because you couldn't be put anywhere else. Ridiculous. Yeah, caffeine has a hell of an effect on me too. I get kind of like a little jittery. I can get like nauseous, appetite suppressed kind of thing. I don't like that about caffeine. I try not to do a bunch. A monster a day keeps the Hat Man away. Yeah, no, I kind of... Wow, his setup is fucking just gushing water everywhere. Jesus, dude. Seal your shit. Hey, we might see an explosion yet. He might fucking cause an electrical problem.
That's the worst.
Yeah, no, I kind of raw dog my days without caffeine for the most part. I mean, sometimes when I'm just didn't have much sleep, I'll have some like tea in the middle of the day, but for the most part, it's just like I don't really like
Of course it's gonna shoot out with the
having the ups and downs of, you know, missing caffeine or missing taurine or whatever other substance of your choice is. It's not my favorite thing. Just would rather have kind of a slow morning and
I don't know if I'm
deal
gonna
with it
survive
throughout the
this one,
day.
if I'm gonna be honest. Okay, I've fixed up the water.
Oh, good. It's not wet anymore.
But I have to know, does it heat? Does it heat?
Yeah, sometimes caffeine's good, but yeah, I don't
Degrees.
make a point out of it to imbibe daily or anything like that. So I don't have a dependence, and it's great. Might have had a dependence when I used to be like a soda a day kind of teenager, but I never really, I don't know, internalized how much caffeine was in those sodas.
What?
Never went for sodas either.
I thought it'd be temperature. But it's just watts.
Oh boy.
5 kilowatts? Christ, that's a lot of power. That's too much power. That is twice what this thing is rated for.
So, don't turn it up that high, Tom.
Why did I buy this? I can't
You
run
were a
this.
huge soda drinker, you got that out of me because college.
spent
I got
far
the
too long
actually the soda drinker was worse for me in college because we had like nice fountain dispensers in all of our mess halls, but in grad school I kind of got out of soda because that suddenly meant I had to A, purchase it, and B, carry it home, and C, without a car in America that's fucked, so I stopped doing that.
about plugs, but here we are. I have something that hopefully works now. I even posted this to Patreon. and I had
Crystal
some
Pepsi.
suggestions
I never
about
tried the
this
remake.
plug. Some people said it might have been
Citrusy,
Australian
it sounds
20
nice.
amp plug, which I didn't even know there was a standard for. I've never seen a 20 amp plug. You know, we've got the 10 amp and then the 15 amp and then all the 3-phase, you know, circular pin ones. Familiar with that. But there's also a 20 amp one, which we thought this one might have been, but it's not even that. It is a Chinese standard. Now, you might say, well, that's obvious now in hindsight, but are 10 amp, as in Australia and China have the same 10 amp plug, but this is a Chinese 16 amp plug, which is not compatible with the Australian 15 amp system. Thank you to the online museum of plugs and sockets for this diagram that shows it just slightly too big, which explains why I could really, if I tried, I could force it in. I changed the plug. Well, my dad changed the plug because I don't trust myself to do that. much.
Yes, his father, who actually has
Cool work.
electrical engineering
Now,
experience.
This will plug into the wall, and I found it's either 10 or 16 on the circuit breaker.
That sucks. That's why. At least that's why I know why I like Pepsi a little more, because of the citrus is nice. But yeah, having a citrus allergy definitely sounds rough. Imagine having a citrus allergy and the cilantro gene. You'd just be miserable.
It's not going to be able to cool itself properly, and all the water that's trapped in there will probably boil, which is an insane way of doing this, by the way. Look at this terrible. I put this tape here, but this thing doesn't sit in here, and you're kind of like, oh,
God.
it's fine, it's 12 volts, but it's not. It's a 240 volt output, which is insane because they're just putting it through a transformer to 12 volt anyway. You could make this output 12 volt, and then you wouldn't have these two 24 volt pins sitting here next to this cooling water flowing through here. Like,
Okay,
that's an
so
insane
this
design.
device
Anyway,
is in
let's
fact
try this
awful,
bad boy out, I
which is
guess.
probably
This
why it was
shocks me even
affordable.
once. I'm throwing it in the bin and ending the video, by the way. This shocks me
Water,
even once.
unnecessary
I'll probably
electrical
die,
conversion.
actually, but
Wait, what the fuck is he doing with the tape?
24 volt pin
I have
sitting
to
here
actually
next
listen.
to this cooling water flowing through here. Like, that's an insane design. Anyway, let's fire this bad boy up, I guess. This shocks me even once. I'm throwing it in the bin and ending the video, by the way. This shocks me even once. I'll probably die, actually. But I'm going to have a 0 shock tolerance here.
Oh, I think he's
My
using the
God.
tape because he can't get the damn plug to actually stay in that well. Oh my god, this is a hell machine.
Alright. Good start.
We already had
I'm
him make
interested in
molten hell in
how
a
hot this
cup
cooling water
beforehand,
gets.
and now he's gonna
This
make it in
cooling
a
water gets
graphite
very, very
crucible
hot very
too.
quickly. We won't be able to run it from a bucket like this. We'll either need a much bigger reservoir or have to run it from something like a hose or something. I have a feeling it's going to get very hot very quickly. So, but just how hot? Is it a manageable hot, or is it going to be?
And he's gonna see how long he can fucking make a
Alright.
an aquarium pump cool down a several thousand degree heater. Oh my god, Tom, this is why I love you. This is a great fucking channel.
Thermal camera. Yeah, alright, it's getting hotter.
Ah, he busts out the sideways thermal camera. Nice.
quite fit because I'm using a slightly different crucible. I've only got one that perfectly fits, which is the one that came with it. I'm going to put proper gloves on. Let's go put gloves on.
You can kind of crash where you can call this guy a bogan sight.
Crucible is glowing hot.
Nice.
Glowing hot already. It's at only at
Again,
2
using the
kilowatts.
Australian
It's been
terms.
about 10 minutes. Oh, these aren't the right tongs for it, but oh man.
Motherfucker has none of the correct equipment for this. This is such a disaster.
The cooling water's doing good too. It's only at 26. It's getting hotter. All right, cooling water's getting to 31. So I think it's all right, but we do need a larger volume of water, and we'll have to change over the water a bit, especially for 6 hours. I still don't think this will run for 6 hours, but mostly I'm curious about fucking ramping this up all the way to 5, right? Let's see if we can melt some steel. How hot is this getting? This is sick. Whoa. We have a chunk of steel here.
Time to
We have
test
a melt point
things.
of about 1,500 degrees.
I guess, yeah, if you can melt the
Let's see
steel,
if
he
we
can do the
melt
reaction he
in
needs
this
to, so.
crucible here. Let's try it out. Got a new bigger bucket of cooling water.
That's right.
Gotta keep that temperature in mind.
I think drinking some wine is a lot better of a fate than drinking corrosive waste. He did do a very, very early video on which alkali metal salt tastes the best, because, like, you know, sodium chloride, that's table salt. Then he and his friends tried all the different chlorides, so lithium chloride, potassium chloride, rubidium chloride, and cesium chloride. They all did do that to season their fries once. I think that's the furthest they're gonna go with ingesting various chemicals. Because some of them were bitter, but they were at the very least safe in small quantities. I think the corrosive waste would be just death. Still sounds kind of cursed. Yeah, definitely, but like potassium chloride is kind of like that, you know, food additive in the less sodium salt that you sometimes see. And it's just like more bitter, shittier salt. And lithium chloride, according to them, had a little bit of a lemony flavor, so kind of nice, I guess.
Lord, oh Lord.
Yeah, if you wanted to prank somebody like that. I feel like I should prank somebody like that. I should have the mystery salts.
Crikey.
Oh, look at that.
It's hot. All right.
Look at the iron sparking.
Setting the
That's
iron
little
on
particles of
fire.
iron entering the air and oxidizing instantly.
Whoa.
Don't surrender the red dye 40. No, it's mine. Of course not. Hey, defective. I think if you poured red dye 40 into this, you would instantly have a toxic fire. Yeah, rush it with alkaline salts.
Burn
It's
into iron.
perfect.
Oh Lord. Yeah, that's molten iron on fire.
You have 1 out of 5 chances you get normal salt, 1 out of 5 chances you get lemony salt, 3 out of 5 chances you get bitter salt. You'll get your yearly dose of rubidium. Alright.
Down in there.
Tom,
Whoa.
don't pour that out into the fucking... Okay, I was about to say, he almost poured that out into, like, the white, like, jacket thing. That would have been a bitch to clean.
Oh yeah, that is molten iron. Well, was molten iron. Guess it kind of kills this one crucible, but I have spare, and it felt safer than pouring
But
this out here when I was
you could-
unprepared. I gotta say, I did doubt it. I was expecting
You
it to
could
maybe
heat it up
slump
again
a
and
bit,
pour it out,
eventually, but
so it's not
within 5
completely
minutes to
ruined.
Melt it like that. Pretty good. Pretty good. Alright, it's a beautiful day to make some yellow.
Oh yeah, he
We
definitely
have
could
everything
make
we
dumb cast
need.
iron
We
things.
have,
I'm pretty sure when we
yttrium
watched
carbonate, we have,
when he watched Nile
strontium
Red do
colored
something similar,
molybdenum
like Nile Red
trioxide and,
was like
off-colored
trying to pour
tantalum
out
pentoxide,
iron, like
and,
form a ring
we need to
or
mix
something
this
like
up,
that,
grind it up,
little
and
ingots.
start heating. And here's this paper here. They first do a preheat of up to
And so you could
600
too, if you
degrees,
just want
which
to
is
create a
maintained for
giant
1
fire
hour,
electrical
and then they
hazard
heat
in
it
your
up to
house, you could
1400
also buy
degrees
one
for
of these
6
things
hours.
off of
There's also
Alibaba.
a lot of ramping time, you know, it's 8 degrees per minute up to 600 degrees and then 10 degrees per minute from 1600 to 1400, which is, you know, a lot of extra time. So this is a full business day worth of heating. We're not going to be able to heat it
Okay,
to 1400 degrees for
can't
6
just go to
hours.
1400
but we can do the
immediately, he has to do
preheating
some
in this
preheating
furnace,
steps.
which, you know, will take some of the work away from that other furnace.
You could also
And
make a
we'll
horse
do
to
this
go with those
preheating
horseshoes
step,
too,
which
D.
I'm going to do twice.
Don't let your,
because we
you
have
know,
this
dreams
extra
be
kind of
dreams.
chemical step we need to do while it's heating, which is this decomposition of the yttrium carbonate to yttrium
Oh yeah, he
oxide.
didn't finish
So
the
I'm gonna
whole
heat it at
metal
600
processing
degrees
thing.
for, say, half an hour,
Lamau.
an hour or so. Take it out, re-grind it, because we've got to do this solid state reaction. So making sure everything's nice and well mixed is important. And then we'll put it back in, heat it back up to 600 degrees, and then go from 600 to 1400 and keep it there.
The world is your iron oyster if you can cast iron.
Degrees. But that's red hot, you know. We're not going to be able to monitor the temperature because it's way above any device I have for monitoring temperature. My thermal camera can measure up to about 550 degrees, and even those IR monitor things don't work above 600 degrees. So 1400 degrees, way too hot. So we're just going to heat it till it's glowing and on the maximum wattage, and then
the good old measurement of temperature by eye method.
We see some yellow. As I mentioned earlier, we're going to make 2 batches, one undoped, so no tantalum, and then one with a 20% tantalum. Of course, if we read the paper, they say
It's clear from the absorption spectra of the samples that the absorption edge of the pigment dramatically shifts to longer wavelengths with increasing doping of tantalum.
So you have your undoped, and then as you're increasing the tantalum, you move this
more little bits of
absorption edge,
tantalum,
so
the
you're
color
absorbing
changes,
more blue
moves
light,
towards
which will make it more yellow. However, when we look at the photos, I know I've already touched on this before, but really, maybe the photos lie and the data's all right, but this is the 20% doped one, and this is the undoped one. And you might say there's a little bit of difference, or maybe it's
saturation
hard with the printing, but this
goes up.
sample here is also an undoped one, and you can see it's the same pile of powder. So there's more difference between the same pile of powder photographed 2 different times than there is between the 20% doped and the undoped.
Might just be a
one.
particle
It's the
size
same
thing
sample,
at that point.
right? We'll find this out ourselves. Who knows?
Actually, no,
if this is
it
even
just
gonna
looks
go
like a
yellow.
photo
We've got white
exposure
powder,
thing.
a weirdly green
Yeah,
powder,
it might not
and
be a
sort
great
of grey
paper.
green powder. Is it going to make something nice, bright, and yellow? Who knows?
I'm excited for the
Who knows?
tantalum doped one just because there's
Let's
definitely
get
still
this
chromium
thing
in
cranking.
there,
Let's get this
and that's going to
bloody
cause
cooking.
some
See if we
interesting
can cook up
colors,
some
I'm
yellow.
sure. Carbonate.
Okay, the stuff's
Ugh.
blended into a paste. The starting materials
What
weren't
the
that
fuck?
wet. They weren't completely dry, but maybe the acidic oxide reacted with the carbonate already. Whatever. We're just going to keep going. I mean, it's going to go to high
What a
temperatures.
fucking
It's just
terrible
hard to
mess.
mix when it's
That-
pasty, but
that
this
looks
ain't
like
stopping
the
us. Do you
cartoon
like my
belly
yellow
lint.
pigment? Are you
That's
impressed by
awful.
it?
Like, I feel like there's a Rugrats episode where, like, some grandfather, like, pulls that shit out of his belly button. It's disgusting. It's probably a George of the Jungle episode doing that, too, but that's besides the point. Oh, Tom, not using pure reagents, not getting up yttrium oxide, you just had to go right to the
10
carbonate.
minutes at 600 degrees.
Fucking terrible
Ooh.
ideas.
Oh, yeah. There's some yellow already.
Alright, well, it's got a little... Okay, I thought at first he waited too long and, like, whatever he made kind of just stuck to the freaking crucible as it cooled down. LED buttons are devices that create free kindling. Yeah, I guess it's full of oils and lint. That's all flammable. It's not very good kindling, but yeah.
Set it to 800 degrees
Or
now.
very abundant
Just a bit
kindling, at
higher.
least.
We'll let it cook at this temperature for a little bit. This is the dope one, looking pretty similar so far. Alright, the undoped one's been at 800 degrees for the last hour or so. Let's get him out and let's get him up to 1400 now. Get this dope one heating in the meantime.
Alright, time to go
Let's
from
go
mini
really
hell
heat
machine
this.
to the real hell machine.
Oh, it's getting really yellow.
That's good.
I don't know if it's just glowing, but seems really yellow in there. Alright, I've preheated this one just a little already. Not that hot, just a little. Start the heating. Just keep an eye on the temperature of the water bath.
I like how he has the water
Don't let that
output
get too high,
still
as we
just
know,
like
but we'll
flowing
get this
in
through.
from the top as if it really needs to have that fountain effect.
1600.
If that knocks over, that's just gonna get water everywhere.
It's still only 2600.
Ooh, look. The pits of hell.
It'll be hot enough already. It looks hot.
Get a fucking proper crucible grabber, dude.
It's hot. Oh, that's bright.
Oh, wow.
Probably fucked my thermal camera, but
Yeah, it's turning your thermal camera to static, man.
That's hot. That is hot. Smoking a lot though, so I'll just leave it like this.
Yeah, you're breathing in delicious metal oxide fumes.
Hot. My goodness. Alright,
Dude is
10 minutes in,
poisoning
and,
himself slowly.
That water as it's coming in, or the return water is steaming a little. I don't know if you can see that, but whoa. Ow. That's hot.
Hot water too.
Hot
Oh
return
god.
water. Alright, we're gonna have to modulate the heating a little and then turn it off for a moment. Alright, the cooling water outlet is only slightly warm now. It's been off for about 5 minutes. Let's get it cranking again. Maybe a little higher.
Yeah, I appreciate the ambition. This is...
Give this a shot. What's it look
I mean, I
like?
think the only thing he's done that's less safe is the bromine synthesis. On a huge scale on the last stream.
Heating button.
That was bad. This is bad too, but like, wow. I mean, pouring giant heaps of bromine everywhere. That's bad. That is bad. This is bad on a different level. Not as intense. But still, nothing I would ever want to see anybody do outside of a professional lab setting. All right, where are you gonna pour it out, Tom?
Oh, I can't look at that. I can't look at it.
It's white hot.
Oh, I need sunglasses. I'm seeing spots, man. That's psycho. All right.
Yeah, black body radiation's a bitch.
Materials. I've got the undoped one, fresh out of the other furnace. This graphite crucible was a lot easier to pick up than this other one. This other one doesn't have the groove in it. Fucking sucks to pick up. It's cooled down a little bit in here. The water's not too hot. Might heat it again a bit later. Give it another round of another burst of heat, but get this other one cooking.
Yeah, if you let
Can't
that...
tell the colour yet. Still just glowing red in there.
Well, I can't see the
Anyway,
red,
this
so...
guy is-
Very unusual decision to just let it cool down in the crucible. It's just gonna get stuck in
Oh,
there.
no.
You should have poured it out on something.
Best of luck to this guy.
I am really curious to see
Steaming again.
what he's gonna pour it out onto, because I get the feeling he did not like purchase a mold or anything that can maybe actually withstand
Yeah.
the high temperatures.
All right. Ugh. We'll give it a moment. We'll give it a moment. All right. It's still heating everything, but this is our undoped one. It's just cooled down enough to see the color. Oh no. Oh no. Hold on. Let me turn the flashlight on.
Color black.
All this work, we fucking burnt this to shit. What the fuck? It was looking kind of yellow. It was looking really yellow. Did we get it too hot? What's happened?
Probably got it too hot.
Absolutely
Probably
cooked this. Oh,
further
no.
oxidized in the
no.
air.
Let's
over
save the other
oxidized.
one. Oh no. That's my whole batch. Oh,
You needed to
no.
cool that down quicker, Tom.
Oh, quick. Oh, God. We've got to stop this. Oh, I hope I didn't cook this one too.
Oh god.
In all my thinking, I didn't think I'd get it too hot. That was not something I thought would happen. Oh no, I barely heated this one.
With no temperature
And it started to
modulation, of
go
course you're gonna get
black
too
too.
hot.
Oh, it was pretty yellow before I put it in the insane furnace.
Tom,
Oh,
don't
no.
despair. It could just be a
Oh, no.
surface of black crust. You might have some yellow powder underneath.
Oh no, all right. I got time for another batch. One more batch. Let's ditch this black stuff. I'll make an undoped batch. Let's just not get it so hot. You can't get it so hot. Oh man. Here's our second batch of undoped. We are taking it all the way up to 1,000. It's already had half an hour at 700 degrees, and then I've took it out
So
and
your
reground
solution
it.
was to
and so
make it
we're gonna see
hotter
hopefully
in
it's stable up to 1,000
the pre-treating
degrees here in this
machine?
furnace, and then we can
I don't
go
think that's gonna
over
do
to the other
anything,
furnace
dude.
if we want to see if we can get it even more yellow. But let's see how yellow it gets after heating to 1,000, because we don't want to overdo it like we did the last batch. Okay, this undoped one has been at 1,000 degrees.
Yeah, I was working to the night.
Let's grab them out. Ooh. And I can't tell the colour because it's just all red hot, but it's basically on fire. Okay. Yeah, cool. All right. Is it on fire?
The fucking graphite's on fire. Amazing. I mean, it is just coal, technically, but like...
I'm gonna let that go. And then I'm gonna get this the doped one heating, and once that stops being red hot, we can actually try and see the color on it. It's looking
Dude,
good.
really
It doesn't
need to
look too
think about
black,
the cooling
but
process a lot
yeah, I can
better.
tell when it's just glowing bright orange like that. Get it away. Oh yeah, see,
Hey,
look
it's
at that.
yellowy. That's good.
That's a fantastic yellow. Well, I mean, it's not quite as vibrant as the paper is, but once again, we've only taken it up to 1,000 degrees, so I do want to take it up higher. My theory is why it went black was not because it was too hot, but because of the graphite. The graphite at 1,500 degrees is extremely reactive and very reducing, so I think it's pulling the oxygen out of the structure, out of the oxides, and reducing it back to the metal. Well, like molybdenum, it's just that.
Yeah, that can make sense. Powdered metals are often
at that temperature. So I really want to move to a different crucible.
grayish
I don't
powders.
really have a nice crucible like this, and I'm not sure if I use a different crucible, will it work in the induction furnace? Does it have to be conductive for it to work? Let's give it a shot. Let's try and do this in a way where we can heat this powder up to the 1,500 degrees or 1,400 degrees or so, just in this thing. But we don't want it to shatter, so we're going to have to take it a little easier. But that's what we're doing. It's obviously getting nighttime, but also have a doped sample cooking. I just had enough yttrium to do a half batch of some tantalum doped one. So let's get this.
Carbon would
still very hot, but
contribute
let's
some
get this
electrons, want to
yellow
form
powder,
CO2 at really high
1,000 degrees
temperatures.
powder into here, and then let's see if we can heat this, you know, with the power in it, up to the higher temperature that we need. Well, that's what I think we need. I don't know. Maybe this is as good as it gets, but I'm getting greedy here. Everything is horribly out of focus, but that's how I'm feeling right now anyway, so it feels appropriate.
Like, Tommy, you didn't wait till tomorrow to do this? Like, you could have done the second part of it during the day when you're not, like, extremely tired. Oh, and he's trying to heat it from the top? No. That's not how an induction furnace works,
The
dude.
heat transfer's so bad that this doesn't even get to 400 degrees. I really need it in there. I need it in the base there, where it's really hot, but how can I do that? Can't put it in
Just
steel
don't
'cause it's
run it
steel
at
and metal,
5,000
melt.
watts? You could run it at a lower
Ports will
wattage.
get fucked up, I think, especially this rapid heating and cooling. I'm going to put this ceramic plug down at the bottom of this. It's all I can think to do. Hopefully it stops a lot of the material touching the carbon, and we can still heat it to a high temperature. That's all
I guess it's a good point. I guess the paper never really specified what vessel material was being used. Stare into the pits of hell until it hurts to look at, and then, you know, that's when you pull it.
Give it a bit of time. I've been pulsing it on and off at the full wattage. You can't see shit on the camera. Oh man, there's so much infrared radiation coming off that the camera sensor is overwhelmed. But I think everything is absolutely cooked except for the little bit that's on the ceramic tile in there. There's a little pile of powder.
Alright,
that
3
hasn't
minutes
touched the
left.
graphite,
Let's see.
but
Did he
has
make a good
been
powder,
getting
or
really
did he
hot, obviously, down in there.
burn it
So,
all again?
Yeah, sorry about all this noise. I can't turn it off because if I turn it off, the water cooling stops, and then it'll die. Anyway, let's let this cool down so we can actually start to see what's in there.
Ooh, that's a cool nighttime shot, though. I can see why he used that for one of his alternate thumbnails.
Oh man,
Oh wait, Tom, that's it. If you want to cool it down quick, just dunk it into the fucking cooling water. You have a whole source of cooling right there.
Yeah,
Hey,
sorta.
that's sorta something.
Yeah.
Some of it's definitely burnt, but that's something.
Dunno.
Well, the important thing is that he tried and made this at home.
And in the daylight here, we can assess the damage. Look how
Oh my
black
god,
this
that's
sample
like
is. We really burnt
Banta
it,
black
but
dark.
If we kept it at 1,000 degrees, the samples didn't stay yellow, even though they looked yellow when they were red hot. And I think they might have actually been yellow. On cooling, they went back to white, didn't retain their yellow color. But we did manage one sample. Look at this. This was a sample that was balanced on a little bit of this crucible.
Look at
Didn't touch
that.
the graphite. Maybe it's not as simple as that. Maybe it just didn't get too hot. So maybe these samples got to 1,500 degrees and that was just too hot and causes decomposition. Whereas 1,400 degrees is hot enough to cause it to
that's
go
yellowish,
yellow, but
so
not enough to make it go
for a
black.
home
Or it's
chemist,
proved the
mission
point.
success,
Even
I'd
if
say.
you think the science is a little bit stupid, doesn't make it easy. Science is still difficult. It's going to be yellow for all eternity. It's been yellow for the last 2 weeks, so it's going to be yellow for all time. There's enough here to do my true purpose for this video. Painting a picture of my cat.
Aw, that's cute.
Alright everyone, I hope you enjoyed this video as much as I did. Well, I'll see you next time.
Aw, adorable little cat. And
Oh,
I've seen his cat before.
I forgot I
Doesn't show it
can't
off so
paint.
much. Nah, it's good. Don't worry about it. Alright, well. I hope you found that as entertaining as I did. I'm blown away by the fact that he decided making molten potassium hydroxide was a good idea for any application. And then that he also bought another insane furnace, so. Well, Tom really outdid himself on this one, methinks. So, I hope you all found it entertaining. And, you know, like, subscribe, all that kind of stuff. We'll be back next week with more Mega Man on Monday. We'll be starting the Doom community streams on Tuesday as well. So, people submitting maps. If you want to submit something, you still got one more day until the end of tomorrow just to go and join the Discord and submit some Doom maps for me to play. So, participate in that if you like. Otherwise, have a good night, everyone, and I'll see you next time. Peace.